What if everything we know about the beginning is actually the middle of a much bigger story? The Big Bang. The moment we were all told was the birth of time, space, and everything may not be the origin at all. It might just be the first visible frame of a far older, deeper, and stranger reality. In this journey, we'll cross the boundaries of physics, touch ancient myths, decode cosmic clues, and ask the question no one dares to answer. Was the Big Bang the end of something else? The Big Bang isn't the beginning you think it is. It's been almost 100 years since the Big Bang, and the term has become almost mythical in both science and pop culture. Everything seems to have exploded out of nothing, like the universe, time, space, matter, and energy all appearing from a single, very small point. A show of fireworks in space that marked the beginning of everything. But here's the catch. That's not really what the Big Bang is. That's not really true. It's just a mistaken idea based on extension. As science keeps digging deeper into reality, one thing is becoming clearer. The Big Bang was not the start as we usually think. In this case, it was the start of something measured, not everything. What do experts mean when they say Big Bang? That will help us understand why. It's not really a blast. It's not something that took place in space. Space itself grew bigger from a hotter, denser state. We use general relativity to do the math and find that the universe gets smaller and denser as we go back in time. About 13.8 billion years ago, we reached a point where those calculations had no more work. A singularity is a place where densities reach infinity and the rules of physics break down. But that singularity is just a logical border. It's not a real thing. But what it really means is that our present thinking doesn't work there. The Big Bang is not a proven moment of creation. It is a time when we don't know everything. General relativity and traditional physics are no longer useful after that point. If someone says, the universe began with the Big Bang, they really mean the universe could be seen after the Big Bang. It's like picking up a book in the middle and thinking that's where the story begins because you can't see the first few pages. One big reason we think there was a hot, crowded state is that we can see what comes after it. The cosmic microwave background, CMB, is a field of microwave energy that forms the background of the universe and is thought to be the result of that state. It was found in 1965 and is still one of the strongest signs that the universe was much hotter and denser in the past. But the CMB doesn't take us back to the beginning. It's from about 380,000 years after the Big Bang. What about the time before? We don't know the truth, but we're beginning to make models that hint at some interesting options. One of them is cosmic inflation, a theory that proposes that, a fraction of a second after the Big Bang, the universe underwent an unimaginably rapid expansion, stretching faster than the speed of light. This would explain why the CMB is so uniform and why the universe appears flat. But inflation itself doesn't explain the origin. It raises even more profound questions. What caused the inflation? What existed before it? Could the inflationary state itself have emerged from something older? There's also a chance that the world never really started in the everyday sense. Space and time are quantized in some versions of loop quantum cosmology. This means that they are made up of discrete units instead of continuous factors. This lets the world bounce instead of bang. It didn't come from nothing. Instead, it shrunk from a previous state, reached its smallest size, and then started to grow again. This view sees the Big Bang as a kind of stopping point, or a cosmic restart, instead of a beginning. Other theories use the idea of the multiverse to say that our world is just one bubble in a much bigger quantum foam that is always forming and disappearing. From this point of view, the Big Bang is a local event. It is not the start of all reality, but just the start of this area of space-time. There's also the more intellectual view that the Big Bang wasn't the beginning of everything, but the beginning of order. There may have been confusion, chaos, or a state of quantum physics that never changed before the Big Bang. The Big Bang didn't start everything, but it did start time as we know it, the chain of events, and the rise in chaos. After that, the world turned into a place where things could grow, change, and be observed. Before that, not a sequence. There are no events, not remembering. This point of view is directly related to how we think about information in physics. A lot of scientists now think that knowledge, not matter or energy, is the most basic thing in the world. The answer of the black hole information dilemma says that information is never really lost. If this is true, then what happened before the Big Bang might still be there, stored in the quantum state of the universe. That means the Big Bang did not erase the past, it squished it. So why do we cling to the idea that the Big Bang was the beginning of everything? Because it's simple, because it fits into the human need for origin stories. It mirrors religious creation myths, a single moment of divine emergence. And because for decades it was the furthest point back that our equations could take us. But science evolves, and the narrative must evolve with it. The universe had no center, but did it have an edge? There was no explosion into space. Space was getting bigger. The Big Bang did not happen in a certain place. It happened all over at the same time. Also, when we ask, where is the center of the universe, or what is on the edge? We're taking our intuitions, which come from living in a three-dimensional world, into the universe, which doesn't work that way. Still, they're fair questions. They tap into something instinctive, something primal. If the universe had a beginning, then surely it started somewhere. Surely it must be growing into something. Surely there's a frontier, a limit, a boundary, an edge. Let's start with the idea of a center. In a normal explosion, there is a point where the energy was released and a space around it where the debris grows. But this comparison doesn't work at all when it comes to the Big Bang, because space itself grew bigger. It's possible that all of space and time were once squished together, but not into a single spot. That means the middle was everywhere. It was everywhere, so nowhere is in the middle. Cosmologists often use the balloon growing as a metaphor to help them understand this. Imagine that there are tiny dots all over the surface of a balloon. The dots move away from each other as you blow it up. But keep in mind that the surface is only 2 dimensions, and the center of the growth isn't on the surface. It's inside the bubble, in a higher dimension. There is no middle from the point of view of someone on the rocket. There is no special place. Everything is going away from everything else. Now use that bubble as an example of something in 3 dimensions. The universe is not growing into anything. It is just stretching. There is more room between galaxies, so they are moving away from each other. This is not because they are flying through space. An edge suggests a boundary, something beyond which the universe stops and something else begins. But if space is all there is, if the universe is the totality of space-time, then asking what's beyond it is like asking what's north of the North Pole. The question contains a false assumption. It assumes a kind of external viewpoint that simply doesn't exist in the way we imagine. And yet, there are models of the universe that suggest it could be finite. That doesn't mean it has an edge like the end of a table. It means that if you traveled far enough in one direction, you could, in theory, loop back to where you started. Just as you can walk around the Earth and eventually return to the same spot. The universe could be a kind of higher dimensional torus or sphere, finite in volume, but without boundaries. From what we can see, the world is flat on a large scale, not bent like a sphere or saddle. That means it might be infinite. But infinity is hard to understand. It's not something we can measure. We only know that the universe we can see is about 93 billion light-years across. After that, the light hasn't had time to get to us yet. It doesn't mean the end of the world. It only means we don't know what's on the other side. So, is there really an edge out there? A wall? A spot where space ends? Not likely. Based on what we know about science, space either goes on forever or wraps around itself. There is no sign of a cosmic border, a wall of stars, or a curve that is sharp enough to point to a terminus. But there is one kind of edge that does exist. The edge of the universe that can be seen. It's not the world itself that sets this limit. It's light or time. Light moves at a certain speed and the world has a set age. In every direction, we can only see about 46.5 billion light-years away. This is not the edge of the universe. It's the edge of what we know. The world goes on after that. We have no idea how. That distance is getting bigger. It's not because the world is getting bigger, but because time is running out. We can see farther as light has more time to get to us. But some parts of space are moving away from us faster than light, because space itself is expanding faster. We will never see any light from those places. They're no longer there. They've crossed the cosmic event horizon. In this sense, the universe does have limits, but not borders. It has views that don't have edges. Even though it doesn't have a core, everything goes away from everything else, as if each point were the starting point. What about the idea that the world has a partner? There are theories that say our world is just one bubble in a huge quantum foam. These theories are most common when talking about the multiverse. There could be other worlds alongside ours, divided not by distance, but by energy states, dimensional barriers, and the lack of a link between causes and effects. But even if that's true, space as we know it still has no outside. Our laws of physics don't extend beyond our bubble. Asking what's outside the universe becomes a matter of speculation. There is no space, no time, no directionality out there in any meaningful sense, unless we can find a way to see through the edges of cause and effect, not just the ones that are far away. That being said, until then, the world is both limitless and limited by what we know, not necessarily by what appears. The cosmic horizon, a visible limit, not a real one. We're not just looking at the stars when we look up at night. We're moving through time. Many millions or even billions of years have passed since the last photon reached our eyes or camera. The light is older the farther away we look. And then we reach a limit. No matter how strong our tools are, we can't see past that point. The cosmic limit, which is also called the visible universe, is that line. Light has had enough time to reach us from that far away since the Big Bang. Many more planets, stars, and space are likely out there, but we can't be sure about any of it. Not because it doesn't exist, but because its light hasn't reached us yet. It's tempting to think of the cosmic horizon as the edge of the universe, but that's a misunderstanding. In truth, it's not a real edge, not a wall or border or boundary that space bumps into. It's a limit of observation, a frontier imposed by the finite speed of light and the finite age of the universe. What lies beyond? Most likely, more of the same. But we can't know, because information from those regions is permanently causally disconnected from us. The universe is about 13.8 billion years old, and light travels at a fixed speed, 299,792 kilometers per second. You might think that means we can see 13.8 billion light years in all directions, but that's not quite right. Because the universe is expanding, the regions that emitted that ancient light have moved much farther away in the time it took the light to get here. As a result, the true radius of the observable universe is not 13.8, but about 46.5 billion light-years in every direction. So the diameter of our observable universe is roughly 93 billion light-years across, and growing. But that doesn't mean the universe itself is 93 billion light-years wide. That number simply defines the bubble of visibility around us. Outside of it, space continues. Galaxies continue. Possibly infinitely, but we are forever cut off from anything beyond that boundary. Why? Because of something called the particle horizon, the distance that light can travel in the age of the universe, taking into account how space has stretched along the way. Anything farther than that is beyond reach, not because of distance alone, but because time hasn't allowed it. The world isn't just getting bigger. Dark energy is making it grow faster over time. In other words, the galaxies that are farthest away are moving faster than light. It's not because they're breaking the laws of physics, but because space is getting longer between us. This leads to the idea of the cosmic event horizon, which is the point past which light from today will never ever reach us, no matter how long we wait. There is just too much space growth for those photons to cover the ground. They're getting farther away into the future. So in a way, the universe is shrinking, not in size, but in access. Over time, more and more galaxies cross the event horizon. They fade from view. They become cosmic ghosts, still out there, but lost to us forever. If the expansion continues, and especially if it accelerates into a Big Rip scenario, there will come a day when only our local group of galaxies remains visible. Everything else will have disappeared. This isn't hypothetical. It's baked into the math of general relativity and confirmed by redshift measurements. We're not guessing. We're watching it happen. So what does the cosmic horizon mean? First, it means humility. Our view of the universe is not total. It's a fraction, a fragment, a window carved by time and light speed. What we call the universe is, strictly speaking, our observable patch, not the entirety of what exists. Second, it means mystery. We have no way of knowing how large the whole universe is. It could be 10 times bigger than the observable portion, 1,000,000 times. It could be infinite. And if it is infinite, then everything that can happen, happens. somewhere, somewhen, even if we'll never find it. Third, it means irreversibility. As more of the universe slides over the event horizon, we lose access to information. This isn't like losing a book or a photo. It's the permanent disconnection of entire galaxies, entire realms of existence. They're still out there, but their light will never touch us again. Finally, it means urgency. The universe is expanding, yes, but our ability to see it is contracting. If we want to learn about the cosmos, if we want to map its structure, test its boundaries, and understand its origins, we're in a race against cosmic time. The longer we wait, the more the universe recedes. Because the cosmic horizon is not an obstacle, it's a reminder. A reminder that the universe is bigger than we'll ever know. That mystery is not a failure of understanding, but the natural consequence of living inside a finite bubble of perception. Beyond the horizon, space may look the same, or it may be wildly different. We may live in a calm, flat patch of a universe with regions far beyond that bend, twist, or even break the rules. We may be part of a multiverse, a quilt of expanding bubbles, each with its own horizon. Why nothing might have been something. There was nothing before the Big Bang. We've all been told that story, but nothing doesn't mean what it sounds like in current science. We can see that the supposed nothingness starts to sparkle with potential the more we look at it. It turns out that the vacuum might not be empty at all. It might be the busiest thing in the universe. The vacuum is not an empty box in quantum field theory. It's a sea of shifting lands that is shaking, uncertain, and full of possibilities. Particles and antiparticles are always coming and going, even in empty space. We have seen this happen in tests, like the Casimir effect, where two metal plates in a vacuum feel a force pushing them together because of quantum activity in the space between them. This is called quantum vacuum fluctuation, and it's not just a theory. What does this mean about how the world came to be? Some ideas say that the world didn't start from nothing, but from quantum nothingness, which is a state of vacuum full of unstable energy. From this point of view, the Big Bang might have been a change in phases, like when water freezes and turns into ice. It's possible that the vacuum decayed into a lower energy state, which released a huge amount of energy and made space-time. Some cosmologies, like fake vacuum decay or quantum tunneling, are based on this idea. Even the concept of zero-energy universes fits into this line of thinking. In these models, the total energy of the universe is exactly zero. Positive energy, mass, matter, radiation, is perfectly balanced by negative gravitational energy. It sounds strange, but it's mathematically elegant. From this perspective, you don't need an external force or deity to kickstart the cosmos. The universe could have sprung from a quantum fluctuation and overall still added up to nothing. But this brings up a logical question. Is nothing really nothing if it can lead to something? Thought and science become less clear at this point. In other words, if a quantum void can make worlds, then it is really a something. It has structure, rules, promise, and impacts that can be measured. It's not a blank page, it's a spring that's full. The more interesting part is that nothing, as we know it, might not even be a real thing. There is no such thing as total nothingness, say some scientists. Even if there is no matter or energy at all, rules, possibilities, and dimensions are still there to support physics. Even if those things only exist in thought, then pure void is probably just a trick that people play on themselves. In the past, philosophers like Aristotle and Descartes argued about whether or not a void could really exist. With particle reactors and equations that hint at universes as things that start in a void, modern physics has come back to the same question. People no longer think that the idea that the universe came from a shaking, half-stable void is just a myth. Scientists are actually looking into it. That means the Big Bang might not have come from nothing. It could have come from the tiniest bit of something, a field without shape, a fabric without structure, or a quiet hum on the edge of being. And maybe that hum sent everything. Atoms, stars, galaxies, and even us. The Big Bounce. What if our universe is a rebound? It's possible that the Big Bang wasn't even the start of anything. A bounce from a universe that came before this one could have caused it. From this point of view, the universe didn't start from a single point of creation. Instead, it came from the ashes of a previous universe that had folded in on itself. If that's true, this circle of dying and rising again might have gone on forever. The Big Bounce theory is the name for this idea. It turns the usual story of the Big Bang on its head. The world doesn't start from scratch. Instead, it goes through endless rounds of growth, contraction, breakdown, and rebirth. Not every bang is the start of something new. The idea has roots in ancient philosophy as well as modern physics. Hindu cosmology, for example, describes the universe as going through endless cycles of creation and destruction. But today, physicists are exploring how such cycles might be embedded in the mathematics of space and time itself. It's possible that the Big Bang wasn't even the start of anything. A bounce from a universe that came before this one could have caused it. From this point of view, the universe didn't start from a single point of creation. Instead, it came from the ashes of a previous universe that had folded in on itself. If that's true, this circle of dying and rising again might have gone on forever. The Big Bounce theory is the name for this idea. It turns the usual story of the Big Bang on its head. The world doesn't start from scratch. Instead, it goes through endless rounds of growth, contraction, breakdown, and rebirth. Not every bang is the start of something new. There wouldn't be fire and light right away, just another incredibly dense, hot, and rapidly expanding state. The new universe may inherit some features of the one before it, certain physical constants, a particular curvature, or even subtle patterns in the cosmic microwave background. Or the bounce might completely randomize the cosmic settings, producing a universe that looks nothing like ours. One of the appealing things about the Big Bounce is that it avoids the singularity problem. In standard Big Bang theory, the singularity is a point of infinite density and zero volume, a mathematical monstrosity where the known laws of physics break down. But in a bounce model, that singularity is never reached. The collapse is halted and reversed by quantum effects, offering a more physically coherent model. There are some issues, though. First, we don't have direct proof from observations of a universe that came before this one. It might not be possible to be sure if the bounce erased the memory of what happened before. Some scientists look for patterns in the CMB, like circle marks or strange statistical events, that might be echoes of past cycles. However, nothing has been proven for sure. Second, time is hard to keep track of. When did it all start in a never-ending circle of bounces? Did it start at all? Or is it really forever, with no start or end and just an endless heartbeat? The entropy problem is another one. Entropy, which is a measure of disorder in physics, tends to rise over time. So why hasn't entropy grown up to the point where a bounce is no longer possible if the universe has been cycling for all time? In some forms of the bounce model, entropy is said to reset or get lessened with each repeat. Some people think that new areas or dimensions step in to clean the slate. The Big Bounce is still one of the most psychologically satisfactory alternatives to the traditional Big Bang, even though it has some problems. It paints a picture of a universe that is always changing and changing again, that never really starts or ends. A world that lives and moves. Was there a universe before this one? Could there have been a world before ours? That sounds like a question from science fiction or theory, but in current astronomy, it's a very important question that needs to be answered right away. Since the Big Bang wasn't the very first event, then something, anything, had to have happened before it. The trouble is that we don't just lack proof. We might not be able to gather it at all. Some ideas say that our universe is the child of an earlier one that either collapsed or changed into ours through a very strange process. What was that universe like, though? Did it follow the same rules of physics? The exact same constants? Or was it something completely different? An alien life whose only memory is the spark that made ours happen? One of the oldest ideas about a past universe is based on the circular model, which says that the universe goes through endless cycles of expanding and contracting. From this point of view, the Big Bang might have been a big rebound, as we've already talked about. Others in the field of physics, on the other hand, think that changes, rather than bounces within the same world, hold the key. Take eternal inflation, for example. In this model, space is constantly inflating, spawning countless pocket universes within a grander multiverse. Our universe may have been born when inflation slowed in a particular region, creating a bubble of relative stability. But if that's the case, what came before that bubble formed? Some physicists, like Sean Carroll, propose that time might stretch infinitely in both directions, with entropy increasing on both sides of the Big Bang. In this model, what we call before and after might just be two directions from a central low entropy point, the Big Bang acting as a kind of temporal pivot, not an origin. Time might not have a beginning, only a center. Then there's the conformal cyclic cosmology, CCC, proposed by Roger Penrose. In this theory, universes follow each other like links in a chain, each ending in heat death before being rescaled and reborn. The radiation-dominated state at the end of one universe gets flattened and smoothed, becoming the low-entropy beginning of the next. There is no big crunch, no rebound, just a kind of geometric metamorphosis. Even if there was a universe before this one, we may never know what it looked like. The transition between universes, whether a bounce, a phase shift, or a dimensional transfer, could erase all information about what came before. It could scramble the cosmic memory so thoroughly that our universe wakes up with no idea of its heritage, a kind of cosmic amnesia. They look for clues, like small marks in the cosmic microwave background, strange angles, or imbalances that could point to structures that were there before. These hints would be like fingerprints from a world that is dying on the walls of a new world that is being born. What do these logical conclusions mean? They're very big. If there was a universe before this one, it makes the idea of creation from nothing less clear. We are not in a world that was created out of nothing. Instead, we are a link in a much longer and more complex chain of life. It changes the way we think about the Big Bang, so that it is seen as a result instead of a cause. Could there have been a unique type of universe? One made of different particles and shaped by strange physics rules? Perhaps. It's possible that our universe got just enough from it to work, but not enough to remember. If there was a world before this one, we need to know what stopped it. Was it a slow burn to chaos? A furious falling apart? A break in time and space? Or was it something we hadn't thought of yet? An ending that didn't go out with a bang but with a change? Entropy reset. Can a dying universe reboot itself? Things break down all the time in our everyday lives. Buildings fall apart, ice melts, and stars burn out. As time goes on, everything starts to become more chaotic. This is what entropy is all about. It is a basic law of physics. It's the same on a cosmic level as well. If you leave the world alone for long enough, it will die quietly, not with a bang, but with a whimper. This is called heat death, and it means that everything has slowed down, spread out, and used up all the energy that could be used. An empty, frozen space. Could chaos start over? Would it be possible for a universe that was dying to start over, with low entropy and no history? It's not just a beautiful thought. Some of the most cutting-edge ideas in astronomy are looking into this possibility very seriously. We need to start with the idea of entropy in order to understand how this might work. It's more accurate to say that entropy is a measure of how many tiny configurations a system can have and still look the same when looked at from a distance. High entropy means that the particles in the world are spread out evenly and there isn't much order. Compared to other universes, ours, which is young and full of stars, planets, and galaxies, it has low entropy. So why is this a problem? Because the early universe was shockingly low in entropy. According to the laws of thermodynamics, that should be nearly impossible. It's like waking up to find your messy bedroom suddenly spotless with no explanation. For the universe to start off in such a pristine state suggests something very strange happened to clean the slate. In cyclic universe models, one idea is that entropy doesn't go away, it just gets less concentrated. If the universe keeps growing, all that chaos will be spread out over an incredibly large area. Then, when the next cycle starts, it does so in a small, clean, low entropy state, either through a big crunch, a big bounce, or a quantum phase change. Think about pulling a snake that's twisted out until it's so long that the knots don't matter, then pulling it back together into a new coil. That's how dilution works. Another approach comes from quantum gravity, where the very fabric of space and time might behave differently at extreme conditions. Some physicists propose that near the Planck scale, the very edge of physical law, the rules of entropy could bend. In this view, a universe approaching heat death might quantum tunnel into a new state with fresh energy, fresh laws, and yes, fresh entropy. A spontaneous reset baked into the mechanics of reality. Then there's the more abstract but equally mind-bending possibility that entropy is observer-dependent. In certain interpretations of quantum mechanics and relativity, what appears disordered to one observer might seem ordered to another, depending on their perspective in space-time. If that's true, then resetting entropy might be less about wiping the slate clean and more about changing the vantage point from which it's being read. Still, none of these ideas have been proven. It's also hard because of the second law of thermodynamics, which says that entropy always rises in a closed system, not an exception. In all of science, that fact is one of the most tried and true rules. What could be done to break or get around it? It's possible that the world is not a closed system. If the universe we live in is just a bubble in a bigger multiverse, then entropy could move between universes, or into or out of higher dimensions. Like emptying a bathtub into a bigger tank, the chaos could be moved somewhere else, making room for a new start. If entropy resets, is it still the same universe? Or does it become something new? Can identity persist across cosmic reboots? Is there continuity or just echo? Time reversal at the Big Bang. Time is like a river. It always moves forward, from the past to the future. What if that flow isn't always there, though? Could it be that time didn't just begin at the Big Bang? What if it split, going into our world and going back into something else? There's more to this than a sci-fi twist. In current physics, especially in ideas that look into the symmetry of time, this is a valid question. There is a strange conflict at the heart of this idea. Time is equal to all of physics's rules, especially those that deal with particles and basic forces. In other words, they work the same way whether time goes forward or backward. Anything that is turned around doesn't break. Then why does it look like the world is moving in a certain direction? When we remember the past, why don't we remember this? Why does cause always come before effect? Many scientists think that entropy holds the key to the answer. The basic rules of nature don't include the line of time, which is our sense of direction. It comes from the universe's move from low entropy, order, to high entropy, disorder. Time doesn't flow. Entropy makes time move. What if, at the start of the Big Bang, entropy was lowest not only in the direction of time we take, but also in the direction of time we take? This model doesn't see the Big Bang as the beginning of a straight line. From the center of that event, time flows in different ways, making it the middle point of a cosmic V. Our world is on one side. The other side, a mirror world that grows and changes backwards in time compared to ours. This idea, sometimes called time reversal symmetry or Janus cosmology, named after the Roman god with two faces, suggests that time may have always existed, but with two directions. And if that's true, there might be another universe out there that looks just like ours, but moving backward from our point of view. Its stars are collapsing into denser forms. Its people remember what we call the future. Its big crunch is our Big Bang. From their point of view, we're going backward. There is no conflict. It's just a matter of point of view. This model also does a beautiful job of explaining the problem of entropy. Both worlds will see time moving forward from their own frames if they both begin at the same low entropy limit, the Big Bang, and entropy rises in both directions. But when looked at as a whole, time is symmetrical and never ends. One of the biggest puzzles in physics is the cosmological arrow of time problem. Some experts think this might help them figure it out. Since entropy starts out very low at the Big Bang and determines the direction of time, why should it only rise in one way? Time reversal at the Big Bang also aligns with CPT symmetry, a cornerstone of quantum field theory, which states that if you flip charge, parity, and time simultaneously, the laws of physics remain unchanged. A universe with reversed time could, in principle, exist and obey all known laws. Unfortunately, this is where the theory gets murky. It's nearly impossible to observe a reversed time universe if it's causally disconnected from ours. If it exists on the other side of the Big Bang, its information is sealed off behind the Planck wall. We can't interact with it, measure it, or verify it directly. Still, some scientists are looking for less direct signs of mirrored symmetry, like changes in the cosmic microwave background or patterns of uneven amounts of matter and antimatter. The idea of this shadow world makes us question what we think we know, even if we never find it. Time might not always go in one direction. It might not be a street at all. It could be a structure with branches, with worlds growing outward like diamonds from a main point. In that case, the Big Bang would be more like a split than a birth. A split in the road where time chose to go in two different ways at the same time. Black hole cosmology. Was our universe born inside one? A lot of the time, people think of black holes as endings, bodies where nothing can get out because of gravity. But what if that's not the end of the story? What if they're the start? Some physicists believe that our entire universe might have been born inside a black hole. Not just a star collapsing in on itself, but a higher dimensional object spawning a baby cosmos at first. But when you look closer at the math, the logic, and the parallels between black holes and the Big Bang, the idea starts to make eerie sense. When a massive star collapses under its own gravity, it can form a singularity, a point of infinite density. Around it is the event horizon, the boundary beyond which nothing can return. This setup feels familiar because it's conceptually similar to the conditions at the Big Bang, a singularity from which everything expands outward. Now flip the perspective. What if from the outside we see a star forming a black hole, but from the inside something very different is happening? Inside, a new region of space-time could be forming, its own universe, cut off from the one it came from. This is what black holes are all about. A black hole in one world could turn into a white hole in another, especially in loop quantum gravity or brain cosmology models. It's like a black hole but backwards in time. A white hole pushes matter away instead of eating it. The matter that was thrown out and grew from a very dense point could be the start of a whole new world, complete with its own space, time, and physical laws. That new universe would not be floating in our space. It would be in a different space-time that is not connected to ours. The black hole looks like the end to us, but from the inside, it's the start. First, it may explain the fine-tuning problem, why the constants of nature seem perfectly calibrated for life and structure. If every black hole spawns a universe with slightly tweaked parameters, then universes capable of producing black holes, like ours, will naturally be the ones that continue to replicate. This leads to a kind of cosmic natural selection, where only the most stable or fertile universes survive. Second, it could help resolve the singularity paradox. In classical general relativity, the universe begins from a singularity of infinite density and zero volume. But infinities in physics usually mean we're missing something. If what we see as a singularity is really a transition point, then the infinite density problem goes away. The black hole becomes a bridge, not a wall. The information conundrum, or the question of what happens to information that falls into a black hole, is also cleared up in a new way. That information isn't lost if black holes make new universes. It's born again and written into the fabric of a new universe. What looks like damage in one world is actually making something new in another. Here's an even stranger idea. What if every black hole in our universe holds a different world? Each one is its own bubble of space-time that changes on its own. That would mean that the multiverse isn't some faraway place, but is actually folded into the structure of reality, like Russian dolls. We can't even look inside a black hole, let alone tell if a whole world is living inside it. This type of theory is beautiful, but it's almost impossible to test, so it's more of an academic exercise than a claim that can be proven. Einstein's field equations can be used to find answers where the inside of a black hole looks like the expansion of a universe, and theories of quantum gravity keep pointing to secret dimensions, cosmic tubes, and bouncing geometries that make it seem like birth and death are two sides of the same gravitational coin. Hindu cosmology and the eternal rebirth of worlds. People used to look up at the stars and try to figure out the big beats of life long before there were telescopes, equations, or particle accelerators. Hindu cosmology is one of the world's oldest and most complex ideas about the universe. Its view of the universe's life cycle is surprisingly similar to what some modern scientists say it should be. The main idea is one that sounds eerily familiar. The world doesn't start and end all at once. It goes through stages of creation, protection, destruction, and rebirth over and over again. According to Hindu cosmology, the world goes through huge rounds called kalpas. Each kalpas lasts 4.32 billion years, which is amazingly close to how old scientists think Earth is. A kalpa is only one day in the life of Brahma, the god who made everything. His whole life is hundreds of trillions of years long. Every kalpa has an end, and the world is destroyed. The next day, it is made again. After this, there is a cosmic night, during which everything breaks down into a state of pure possibility. The cycle then starts all over again. It is more than just poetry. It fits logically with ideas like the Big Bang, cyclic cosmologies, and even conformal cyclic cosmology, which say that worlds start over, change, die, and start over again in a never-ending cycle. The Trimurti, Brahma the creator, Vishnu the preserver, and Shiva the destroyer, mirror the three critical phases physicists imagine in a cyclic universe: initial conditions, sustained development, and entropy-driven collapse or transformation. The destruction is not punishment, it's preparation. Shiva's dance of destruction is also a dance of renewal. One striking detail in Hindu texts is the idea of multiple universes, each with its own timeline, characteristics, and fate. This aligns with multiverse theory, where countless bubble universes exist in parallel, each potentially governed by different physical laws. The Bhagavata Purana even describes cosmic eggs, Brahmandas, within which entire universes reside. Each is born, expands, collapses, and is reborn. Sense a pattern? Some readings of modern physics say that our universe could be just one in a long line of universes that were made after a collapse, as a fluctuation in a quantum vacuum or by a black hole. The specifics are different, but the pattern, being born, existing, dying, and being born again, is the same. In Hindu thought, the idea of time that has no beginning or end shows up. Who really knows where the universe came from and when? Is an open-ended question in the Rig Veda, which is one of the oldest holy books. The tone isn't set in stone. It's just an idea. It likes mysteries, a lot like cosmologists do when they look back at the Big Bang. And let's not forget the concept of Maya, the idea that what we perceive is not the ultimate reality. In Hindu philosophy, the universe is a kind of illusion or projection, layered over a deeper, truer reality. Sound familiar again? Holographic principle, simulation theory, and other speculative models in physics hint at similar themes, that what we observe might be a lower dimensional projection of a more fundamental realm. Of course, Hindu cosmology isn't science in the strict sense. It wasn't developed through experiments or peer review, but it was born from deep reflection on cycles, impermanence, and the flow of time. And in many ways, it anticipated questions that scientists are only now beginning to ask with serious tools. It's not that old myths were always right. What makes this comparison strong is that people's intuition keeps coming back to the same patterns across countries and ages. Time without end, cycles in space, over and over, universes are born in fire and silence. And maybe this is the lesson. There isn't always a clear line between myth and science. Old stories can sometimes shed light on new ideas. For some reason, the far future in astronomy can look a lot like the far past in faith. The Phoenix Universe, Brains that Collide. In the story of the Phoenix, a beautiful bird burns itself to ashes and then rises from the ashes to live again. Think about that story being written all over the universe. That's what the Phoenix Universe theory is all about. It's a bold idea in modern physics that says the universe doesn't come from nothing, but from collisions. This idea is based on the idea of brain cosmology, which comes from string theory. In these models, the world we see, space, time, matter, and light, is contained within a huge, bendable membrane, or brain, short for membrane, that floats in a space with more dimensions. Picture our world as a big flat sheet. We're not alone, though. These ideas say that there might be other brains or parallel worlds out there just beyond our reach. Each one would have its own set of rules for physics and would be locked in a secret reality. Until they do, these brains don't normally talk to each other. In the ekpyrotic model, from the Greek word ekpyrosis, meaning conflagration, our Big Bang was not a unique beginning. It was the result of a catastrophic collision between two such brains. The energy released in this impact didn't just light the sky, it ignited space-time itself, sending ripples of matter and energy cascading outward. Our universe was forged in that moment, like sparks from colliding swords. But now it starts to repeat itself. The brains don't hit each other once, just like the Phoenix. They slowly move back together as gravity works its magic. As the brains crash, split apart, and crash again, a new universe is born with each collision. Growth, shrinkage, impact, and life are beating in space. From this point of view, the world has always existed, but its shape has changed over time. Every time two brains collide, one universe stops and a new one starts. And like the Phoenix, each new life brings memories of the old one. The Phoenix universe is very interesting because it answers some very important questions about the universe. First, it addresses the initial conditions problem. Why did the early universe have such low entropy and such a smooth distribution of matter? In brain models, each collision resets the universe, smoothing out irregularities in the process. The chaos of the previous universe is burned away, leaving clean conditions for a new cosmos to grow. Second, it may offer insights into dark energy, the mysterious force causing the accelerated expansion of the universe. Some versions of the theory suggest that what we perceive as dark energy is actually the residual force between brains, subtly pulling them back together for their next encounter. And third, it raises the thrilling idea that the Big Bang wasn't unique. If the brains have collided before, and will again, then we live in a universe that's part of a larger rhythmic structure, a cosmic metronome ticking through time. Of course, there are challenges. Brain cosmology requires extra spatial dimensions, which we've yet to detect. The theory also hinges on the accuracy of string theory, a mathematical framework still lacking experimental proof. And like many ideas in theoretical physics, direct evidence is frustratingly elusive. Some scientists are looking for small hints, like certain patterns in the cosmic microwave background or gravitational waves that might have been caused by brain crashes in the past. If these signs are real, they might be like cosmic fossils that tell us about universes that lived and died before our own. If there are brains and other worlds inside them, then we are not alone. Another world could be drifting next to ours right now. It would be quiet, invisible, and impossible to know, ready to hit each other, ready to start another journey. Roger Penrose and the Echoes of Previous Universes. Sir Roger Penrose, winner of the Nobel Prize and one of the most creative minds in modern physics, doesn't think the Big Bang was the start. He thinks it wasn't even that special. His big idea, called conformal cyclic cosmology, CCC, says that our universe is just the most recent in a long line of universes that may go on forever. Everyone dies. One thing dies, and something else is born. This is how it works. Penrose's CCC theory starts at the end of the world, not the start. According to normal cosmology, dark energy will keep the universe growing until it turns into a cold, empty void, which is called heat death. Black holes disappear, matter breaks down, and everything spreads out so far that there is no longer any structure. In any real way, time stops being important. When everything is gone, radiation, which is made up of massless particles, like photons that don't know time or size the way things with mass do. If there are no clocks, tools, or matter, there is no way to tell how big something is in 3D geometry. Penrose says that at that point, the cold, stretched-out end of one universe is exactly the same as the hot, dense start of another. It's not a bounce. This is a handoff. Penrose thinks of each universe as an eon, and the Big Bang is just the smooth, scale-free link between them. There is no one point, no button to reset. It's just a never-ending pattern of growing, dying, and rebirth, with each world giving way to the next like waves hitting the shore of time. Penrose says it can be tested, and that proof is already out there. He points out features in the cosmic microwave background, CMB, especially concentric rings that he thinks are Hawking points. These are the remains of supermassive black holes that exploded a very long time ago. After living for almost an infinite amount of time, these black holes would finally disappear due to Hawking radiation. Penrose thinks that this process leaves marks in the CMB in the form of circles. Penrose said that these rings are echoes of the death of a previous world written into our sky. This claim is very strange, and not all scientists agree with it. Some people say that the rings that are thought to be in the CMB are just statistical noise or random events. Some people don't agree with how CCC uses conformal geometry or how it deals with chaos. Penrose, after all, says that entropy can simply restart itself, which is still one of the hardest ideas in thermodynamics. Yet even skeptics admire the elegance of the model. CCC offers a framework in which time never truly begins or ends. A universe need not be cradled in mystery at its start or vanish into meaningless expansion at its finish. Instead, each universe lives out its life, and then passes the torch, via mathematics, via geometry, via the very shape of space-time itself. In CCC, we are living not in the first universe, but one of many, possibly not even the most complex or long-lived. Perhaps there were eons with different physics, different galaxies, different civilizations, now erased, except for faint imprints in the radiation that surrounds us. It reframes our cosmic story entirely. We are not the lucky outcome of a single miraculous bang. We are the latest bloom on a tree that has been growing forever. Roger Penrose's ideas may be controversial, but they represent something vital, the refusal to accept finality. Even in death, even in decay, there may be structure, meaning, and rebirth. The egg theory. Was our universe laid by another? Once in a while, a simple story catches the attention of millions of people, not because it answers problems, but because it changes the way they are thought about. One of these stories is Andy Weir's short psychological story, The Egg. It gives a bold view of the universe in just a few hundred words. What if the universe is an egg, and we are all just different forms of the same soul growing towards something we can't understand? A parable about reincarnation, empathy, and universal consciousness. But when taken through the lens of modern physics and speculative cosmology, the egg theory becomes more than just allegory. It becomes a launchpad for profound questions about origin, identity, and the nature of reality itself. Let's begin with the metaphor. In the story, a man dies and meets a being, possibly God, who explains that he is not just himself, but every person who has ever lived. Time is an illusion, and the universe is an egg, a nursery, designed to help this single consciousness mature until it's ready to be born into something greater. Put that into terms of physics now. Could the world be like a place where eggs are being grown? A safe, contained space with perfect physical rules, standards, and starting conditions, not just for life, but also for the development of consciousness? To put it another way, the egg isn't just a creative idea, it's a cosmic design rule. Some thinkers and scientists have thought that universes might be set up to get certain results. In multiverse theories, there are an endless number of universes with different conditions. We live in one where the conditions are just right for structure, chemistry, biology, and finally minds. But what if our universe wasn't a statistical fluke? What if it was created deliberately or shaped through some unknown natural selection process, like a womb, not an accident? Another idea that fits in well with this one is cosmic natural selection, which says that black holes create new universes with slightly different physical rules. Over time, there are more and more worlds that are better at making black holes, which are called offspring. Though it's just a guess, it seems like universes might evolve over time. Could this process lead to a universe that is just right for thought, not just stars and atoms? Panpsychism is another idea. This is the belief that awareness is a basic part of the world, not just something that happens in our brains. From this point of view, the world isn't just a place where awareness could grow, it's consciousness itself, in its earliest stages. Everything, galaxies, particles, and dark energy, might be a part of a growing understanding that we don't fully understand yet. What does the world hatch from if it's an egg? Is it a better kind of life? A super-thinking mind? A meta-consciousness made up of all the ideas, memories, and patterns that have been formed over billions of years? Some futurists talk about a singularity where human and machine intelligence merge. Could this be a part of this natural path? The egg might not hatch at all, though. It might not be about what's outside the shell, but what's inside it. Growth, having multiples, looking back, a cosmic mirror house where billions of living pieces break apart and teach the world about itself. We can't do an experiment to show that we live in a world made for growth, or that we're all parts of the same soul. But proof isn't what holds the egg theory together. Resonance is. It's about something deeper. The need for harmony in a universe that is broken up. The hope that this big cold world doesn't have no meaning, but does have a purpose, maybe not in a religious way, but in a structure way. Like a seed holds a tree, like how an egg holds a life. The idea that the world is changing, that it has stages, a direction and depth, may not be too far from the truth, whether we're talking about physics, philosophy, or something else. And if that's true, then the Big Bang might not have been a bang at all. Did a quantum collapse trigger the Big Bang? When looking at nature at its tiniest levels, things act in very strange ways. Particles don't stay in one place. They move around in a cloud of possibilities. Things don't happen until someone sees them. As well, even something as small as a number can change the way things are. If the Big Bang wasn't a fiery explosion from nothing, but rather the result of a quantum event, what would that mean? In particular, a quantum breakdown. In quantum mechanics, particles are described by wave functions, mathematical expressions that contain all the possible states a system could be in. A photon, for instance, might be in two places at once, or spinning in opposite directions simultaneously. But when we observe it, when the system interacts with something else, the wave function collapses, and the particle assumes a definite state. Before the Big Bang, the universe may have existed not as matter, space, or time, but as a cosmic wave function, a field of pure potential, suspended in uncertainty. Every possible universe existed in superposition, countless timelines, laws of physics, geometries, all coexisting in an unrealized state. Like a quantum breakdown, waves in the universe picked one way to follow. The clouds cleared up and reality set in, which brings about the act of turning promise into reality. That was the beginning of time. Not an explosion, but a choice. Some more complex ideas about the early universe, especially those based on quantum cosmology, agree with this idea. Some people think that the universe is made up of quantum systems that are not controlled by traditional physics, but by a global wave function. In this case, the observer is not an aware being, but the conditions of the system itself, such as relationships within the system, breaking of symmetry, or vacuum instability. A particularly elegant version is the Hartle-Hawking no-boundary proposal, which imagines the universe as a closed quantum system with no distinct beginning or end. Instead of a sharp point of creation, space-time emerges smoothly from a timeless quantum state, like a bubble forming in still water. In this model, the Big Bang is not a singularity, but a quantum transition. The idea of quantum tunneling is another one. Particles can tunnel through energy walls that they usually couldn't get through in quantum physics. In the beginning of the universe, there may have been a tunnel that went from a high-energy nothing state to a lower energy state where matter and growth were possible. Making that tube would be the start of space-time. To put it another way, our world may have come into being by quantum leap. All of these ideas agree on one thing. The universe didn't come from classical nothingness. Instead, it came from potential, which was governed by laws that are basically quantum. It was an event where chance turned into truth, where the abstract became real. Who or what collapses the wave function? Does it require an observer? Or is observation itself an emergent property of quantum systems at scale? If a universe exists in a state of pure probability, what makes it choose to become real? Some experts think that collapse happens automatically, without being noticed, when quantum systems interact with their surroundings. Others use the many worlds interpretation, which says that there is no collapse at all, and that all possible worlds do happen, with each one branching off in its own path. In that case too, our branch had to start somewhere. The point at which the clouds turned into something solid, when existence became clear, that's when the Big Bang happened. The inflation multiverse, endless bubbles, endless beginnings. People often think of the Big Bang as a one-time event, like the curtain going up on our whole world. Some ideas, though, say it wasn't the start of everything. Our bubble was just getting started, one pop in a never-ending foam. Because in the crazy world of cosmic inflation, the universe doesn't start, it grows. In the inflation multiverse, Big Bangs happen all the time, everywhere. To understand this, we need to go back to the idea of cosmic inflation, a theory proposed by physicist Alan Guth in the 1980s. According to inflation theory, the early universe underwent a period of exponential expansion, growing faster than the speed of light for a tiny fraction of a second. This burst of expansion smoothed out the universe, solved the horizon problem, and explained why everything looks so uniform on large scales. But inflation isn't just a side effect of the Big Bang. It lasts forever in many types. In other words, the process of inflation doesn't stop all at once. Other areas keep expanding while one area, like ours, stops expanding and settles into a world full of matter and energy. These swollen pockets keep having the same thing happen over and over again. As a result, a world that is always expanding, made up of bubble universes, each of which began with its own Big Bang and has its own set of rules, constants, and fate. We only have one bubble. This idea is known as eternal inflation, and it has huge effects. It argues that the universe is not a single cosmos, but a cosmic foam, which is a huge patchwork of universes that keep forming from a background of space expanding. There may be places where gravity is stronger than others. There are times when atoms might not even form. Some universes might end right after birth. Some may last forever, but they will never make stars. It's just right for life to exist in our bubble, not because that's how it was meant to be, but because life could only start in that kind of bubble. Our existence in a universe that allows life is based on the idea that we could not live in any other universe. This is the essence of the anthropic principle. We are not the main part of a plan, we are the result of choice. However, endless inflation is more than just a stretch of the mind. It changes the way we think about the Big Bang. The Big Bang wasn't a one-time event in this model. It happened in a small area and was part of a much bigger system that is still expanding beyond the edge of our galaxy. The edge of our world is really just the edge of our bubble. There are many more that are beyond it, which we can't see or reach, but they are potentially real. Some scientists even say that this multiverse might be possible to test. In the cosmic microwave background, if two bubbles hit each other very long ago, they might have left a bruise or a small mark. Teams have been looking for these signs by looking at the sky for patterns in the sky that don't fit with what we normally think about inflation. The proof we have so far isn't clear, but the search goes on. Of course, not everyone is convinced. Critics argue that if other bubbles can never be observed, then the theory flirts with the edge of science, drifting into metaphysics. After all, how can you prove the existence of other universes if you can never interact with them? But the strength of the inflation multiverse lies not just in what it predicts, but in what it solves. It explains why the universe is flat, smooth, and homogeneous. It offers a mechanism for generating diverse physical laws, and it reframes the Big Bang not as the birth of everything, but as the local awakening of a single region within a much larger, eternal process. The end of one, the birth of another. Multiversal recycling. What takes place when a world ends? Does it go away and be quiet? Or could its death be the start of something new? Death isn't a full stop in ideas of the universe that are always growing. It's a comma, a break before the next sentence starts. Welcome to the idea of recycling in more than one universe. The universe, rather than fading into oblivion, passes something on, its matter, its energy, its patterns, into a new domain. A new bubble, a new cosmos. In some versions of this theory, universes spawn successors through extreme events. A universe approaching heat death, where all energy is evenly distributed and no work can be done, might seem like the end. But quantum theories propose that even in this dead state, rare fluctuations could occur. Given infinite time, quantum tunneling could generate a new burst of energy, igniting a fresh Big Bang in a different vacuum state, a new universe with a different structure. Other models imagine that when a universe collapses, say through a big crunch, it doesn't simply disappear. The collapsing matter and energy might reach a critical density, triggering a bounce or transition. This would allow a new universe to emerge, carrying with it the gravitational imprint, or even the information, of the one before it. Some theories go even further, proposing that black holes are engines of creation. Every time a black hole forms, it could pinch off a section of space-time and birth a new universe inside. If that's true, then every galaxy, every dying star, could be a cosmic seed. And just as universes die in the collapse of stars, they're born again in the depths of gravity. This kind of multiversal recycling doesn't just solve a mystery, it reframes it. It suggests that the laws of physics, the constants we observe, and even the presence of life might be influenced by what came before. Universes that are good at surviving, at forming stable structures, or producing more black holes, may end up reproducing more successfully in the grand cosmic ecosystem. This concept echoes a fascinating proposal known as cosmological natural selection, or fecund universes theory, introduced by physicist Lee Smolin. In this model, universes that produce more black holes give rise to more offspring universes. Over time, the multiverse is filled with universes fine-tuned not for life per se, but for replication. Our universe isn't a chance accident if this is true. It comes from a parent. It may have stable, wide, and structured traits that it got from the things that came before it. And the black holes we see spread out in galaxies? They might be the wombs of future worlds, with each one having a slightly different plan. Multiverse recycling is another way to look at cosmic death that makes you feel better. In the old view of cosmology, the universe dies by itself, by being frozen, stretched, or crushed. But in this view, birth and death are always linked. Every ending gives birth to possibility. Every failure leads to growth. And maybe the universe grows back after chaos, just like woods do after a fire. There isn't a camera or monitor that can look into another universe or pick up gravitational waves from a dead universe. But scientists and artists are still moved by how beautiful the idea is. In this model, the world doesn't worry about death. It gets stronger with it. One bubble bursts, one balloons up, one stage in space goes dark, one of them lights up. We are the debris of a greater collapse. What if everything we see, stars, galaxies, even us, isn't what God made, but the leftover pieces of a big cosmic explosion? More and more scientists are looking into the crazy idea that the universe wasn't empty at the start. It started as the mess-up, the field of garbage, the broken pieces of a much older and bigger fall. This sounds like science fiction at first look, but from a science point of view, it's a good question. Could our universe be the result of the death of another universe? If our universe had a beginning, that implies something changed. Some state gave way to another, and change on cosmic scales often means instability. Something collapsed. Something broke. Something reached the end of its line. In this model, the Big Bang wasn't the first moment of space-time. It was the transition point between one state of the cosmos and the next. And the matter we're made from, the radiation that fills the sky, the structure of the universe itself, these might be the ashes, the lingering smoke from a fire we'll never see. This idea is supported by more than one theory. A vacuum decline is one idea. According to quantum field theory, the vacuum of space might not really be the state with the least amount of energy. It could instead be a fake vacuum, or an unstable stable peak. The laws of physics would change if the world went into a lower energy state and then came out of it. Some models say that our universe is that lower energy state that was created when another universe fell into this one. We are actually living in the bubble that was made when that fell apart. Other theories look at the entropy problem. Our universe started in a surprisingly low entropy state, a situation that seems statistically unlikely, unless, of course, that state was the residue of a much larger system. In this view, the orderly beginning of our universe might be the cooled, compressed core of something far messier, a cosmic leftover scraped from the bottom of an older reality. There's also the brain collision model, where two giant membranes in higher dimensional space crash into each other, triggering a release of energy that we perceive as a Big Bang. But what if only one brain was destroyed? What if the universe we observe is built entirely from the scattered debris of that collision? Then our cosmos is a fragment, a scar, a memory of violence. Even black hole cosmology feeds into this idea. A collapsing universe could, under the right conditions, form a black hole, not in its own space, but one that births a new universe in another dimension. That newborn universe may carry with it traces, patterns, energy distributions, subtle imbalances from the dying world that birthed it. If our universe is the junk of another, we might never be able to figure out what that other universe looked like. When you crumple something, it jumbles information. It changes how things work. We have to put together pieces of history to understand it, like trying to figure out what a vase is made of by looking at its broken pieces. There are small imbalances in the cosmic microwave background, cold spots for no reason. There are small gaps between matter and antimatter. They might not be there by chance. They could be the remains of a deeper, older breakdown. What does this mean for us? That means we might not be the big act. We might be what comes next. The second part, a restart that wasn't caused by making something, but by failing. We are the survivors of a disaster we didn't see happen. We are the children of a universe that broke apart so that we could live. Simulation termination. Was our universe a system reboot? You may have heard this idea before, maybe on a late-night show or somewhere on the internet buried in memes and crazy stuff. What if the universe is a simulation? What if we go one step further? What if the Big Bang wasn't the beginning of reality, but the return of a fake one, a crash in space, and then a new boot screen? Simulation theory isn't just a pop culture fantasy. It's taken seriously by thinkers like Nick Bostrom, Elon Musk, and many physicists who've noticed suspicious mathematical patterns in the universe. At its core is a simple argument. If advanced civilizations can simulate universes, and if they run many such simulations, then statistically it's more likely that we're in a simulation than in the one real base universe. Picture a society that is so far ahead of us that they can run simulations on a universe-wide basis. They might be simulating worlds to learn more about physics, evolution, or awareness. Now let's say that one of their models crashes, either because it's not stable enough or because of a mistake in the processing. That crash, that bug, that moment when the fantasy world goes dark and starts over, The universe didn't start from nothing in this case. It started from code, because the directions were changed or because a previous build was messed up. Our idea of a singularity as a blast from the beginning of time could actually be a system-level reset. A program was erased and then started up again. Take the fine-tuning problem. The constants of nature, the strength of gravity, the charge of the electron, the expansion rate of the universe are set at precisely the values needed to produce complexity in life. Why? In a simulation, they'd be parameters, values chosen by a programmer. Maybe this version of the universe was retuned to optimize for certain outcomes: stability, self-replication, or sentient life. Then there's the cosmic censorship hypothesis, the idea that the universe hides singularities behind event horizons. In simulations, errors are often sandboxed, isolated from the larger program to prevent corruption. Could black holes be cosmic firewalls, hiding system-level breakdowns? Even quantum indeterminacy has parallels in computation. In quantum mechanics, particles exist in multiple states until observed. In computing, a pixel isn't rendered until it needs to be. In video games, distant environments are procedurally generated only when the player gets close. It's efficient, resource-saving, just like our universe seems to be. Was there a game before, a messed-up reality, a world where all the rules have been played out? It's possible that the world got too disorganized, unstable, or broken to keep up. It was wiped, done, set up again with new settings and limits on memory. The Big Bang wasn't a birth, it was a start over. Simulations can be stopped. Some people think that as technology gets better, we raise the chance of becoming self-aware, but not in the human sense. They think we become more self-aware in a cosmic sense. A trigger could be set for when a computer starts to doubt its own existence or get close to information that could hurt its purity. A kill switch, a command to shut down. There have been many restarts of the world, but each time, the people who live there get too close to the truth. Could we be in simulation 4.0, where too much was learned by 3 previous civilizations? All of this is, of course, just a guess. It's not clear that we're in a game. There is no space pop-up box. You can't hack the source code, but there are some bugs. Numbers that don't change and look too neat. Resolution boundaries that are like those in digital, such as Planck time and Planck length. The universe acts like math first and then like reality. Could consciousness precede the Big Bang? We've used math, radiation, geometry, and quantum foam to try to figure out how the universe came to be. If we look in the wrong place, what will happen? What if awareness wasn't coming from the world at all? What if it was already there waiting? It's possible that awareness came before the Big Bang. This idea isn't just a spiritual thought. It's a question that's being whispered more and more in the rooms of theoretical physics and philosophy. Could being aware be more basic than matter? Consciousness is something that happens when the brain gets to a certain amount of complexity, according to most science models. To begin, the universe does exist. After that, stars, then the planets, then the molecules, then nerve cells, then brains. This story says that becoming aware is the last step in a long physical process. Some interpretations of quantum mechanics, like the von Neumann-Wigner interpretation, suggest that observation collapses the quantum wave function. In other words, the universe remains in a superposition of possible states, until a conscious observer interacts with it. Without observation, reality stays probabilistic. But with it, reality crystallizes. How did reality start if there was nothing to observe before the Big Bang? Because of this, it's possible that awareness is the observer that caused the crash, that the world, in all its complexity, might have needed a mind to turn it on. It's not a brain or a person, but a basic, vague awareness that is the source of everything. In Eastern beliefs, like some types of Vedanta and Buddhism, mind is seen as more important than matter. In these beliefs, the world is a dream that is made by a single field of awareness. These old ideas are starting to show up in modern science. It's not that it wants to, but the numbers are pulling it there. There's also panpsychism, the idea that consciousness is a property of all matter, not just brains. In this view, every particle, every atom contains a sliver of awareness. The universe didn't develop consciousness, it's made of it. And when enough complexity arises, those tiny seeds of awareness combine into full-blown minds. So if awareness is embedded in all things, and if time itself is emergent, then consciousness could very well exist outside of time. And if that's the case, then it wasn't born in the Big Bang. It may have been the cause. There are even physicists who propose that consciousness is a quantum field, just like electromagnetism or gravity. It interacts with matter, evolves, and perhaps even shapes reality. If such a field exists, then it could have existed before space, time, or particles. It could be the substrate from which the Big Bang unfolded. Then, there's the idea of a universe that looks at itself. Some models say that the universe is a closed loop, which means that its start and end are linked. When consciousness comes into being, it looks backward and brings its own beginning into being. It works like a feedback loop. Thoughts make the universe possible, and the universe itself comes into being. Something like a universal Mobius strip of reality and awareness. Of course, these ideas are thought to be wrong. They question the very basis of Marxist science. There is no way to look for awareness in the CMB, and there is no way to show that it was there at t=0. But the mystery of the observer remains. Why does the universe seem to need awareness to manifest? Why do we exist at all in a universe perfectly balanced to produce consciousness? And if everything before the Big Bang is hidden from view, how can we rule out the one thing that exists within us all? The axis of evil, a glitch from a previous reality. At first glance, the cosmic microwave background, CMB, seems to be a perfect example of how to make something look even. It's the universe's oldest light, radiation left over from about 380,000 years after the Big Bang. It's spread out evenly across the sky, with only small changes that gave rise to galaxies billions of years later. There is a flaw in that perfect glow, though, a pattern that shouldn't be there. It is known as the axis of evil by scientists. It's a real and disturbing oddity in the picture of the first light from the universe. Some people think it might be a mistake from a past universe, a wrinkle in space-time that got caught when our universe was born again. In 2005, researchers looked at data from the Wilkinson Microwave Anisotropy Probe, WMAP, and found the axis of evil for the first time. They saw that some big changes in the CMB, mostly the quadrupole and octupole moments, were lined up in a strange, straight line. Standard astronomy says that these temperature trends should be spread out randomly, but they were all pointing in the same direction. In the standard model, the universe is isotropic, the same in all directions. The CMB, which is essentially the afterglow of the Big Bang, should reflect that randomness. But this alignment suggested a preferred direction in space, and that breaks one of cosmology's most sacred assumptions. The name Axis of Evil was a tongue-in-cheek reference to political rhetoric, but the implications were serious, because if the universe has a preferred direction, then the Big Bang might not have been as symmetric as we thought. Something might have pushed or shaped the universe at its birth. Something from before. Could it be the imprint of a prior universe? A leftover gravitational wave from a collapsed cosmos? A fold in the structure of space-time passed down through a cosmic bounce? Theorists began to speculate. One idea is that this line is the mark of a bubble impact. In models of eternal inflation, different parts of the multiverse can hit each other as they grow. There could be a sign in the CMB that shows which way the universe went if it ran into another bubble early on. The axis of evil could be that point of contact's shadow. Another idea connects the strange event to topological defects, which are flaws in the fabric of space-time that formed as the universe cooled down, similar to how cracks form in ice. It's possible that these flaws are leftovers from a phase change that happened in a world before ours, and were brought to this one through a bounce or quantum reboot. Some even speculate the axis is evidence of a rotating universe. If the cosmos as a whole had angular momentum at birth, perhaps inherited from a collapsing predecessor, That spin could manifest as an alignment in large-scale structures. What's wrong? The info is not clear. The axis of evil was proven by the WMAP and later the Planck satellite missions, but it's not clear if it's a real part of the universe or just a statistical error made worse by nearby pollution, like radiation from our own galaxy. Even though known influence has been taken into account, the alignment still doesn't go away completely, because there must be something very strange going on if the axis of evil is real and not just a myth. Either what we think we know about the early universe is wrong, or what we see is a piece of a different world that made it through the change to ours. The cosmological constant problem, clue to a broken past. Among the many mysteries the world has left behind, one stands out for being so stubborn, a number that is so wrong and so incredibly small that it could destroy everything we think we know. It's called the cosmological constant, and it could be proof of a broken past, a flaw from an earlier state of the universe that didn't go away completely when our universe started. The cosmological constant, often represented by the Greek letter lambda, is the value Einstein introduced to balance his equations of general relativity. Originally, he used it to create a static universe model, before we discovered that the universe is expanding. He later called it his biggest blunder. But the term made a comeback when scientists realized the expansion of the universe wasn't just continuing, it was accelerating. Something out there is pushing galaxies apart faster and faster, and the cosmological constant is the placeholder we use to describe that force, what we now call dark energy. Quantum field theory, which governs the behavior of subatomic particles and energy in space, predicts a vacuum energy density that should act just like a cosmological constant. But when physicists actually run the numbers, the predicted value is about 120 times larger than what we observe. The math behind it is by far the most inconsistent in all of physics, the wildly wrong statement that has ever been made. There is something very, very wrong. It's possible that the vacuum energy was really that high at one point in time, but then something happened. It went down to almost zero because of a change, a breakdown, or an entropic shift. It's not quite zero, but it's low enough that structure, galaxies, and life can start to form. This leads to the idea that our current vacuum state is metastable, not the true ground state, but a kind of plateau, a leftover quiet space sitting atop a much deeper energy well. If our universe fell into this lower energy state from a previous higher energy one, then the absurdly tiny value of lambda might be a kind of residue, an echo of a prior vacuum. It also connects to the concept of vacuum decay, a catastrophic shift that could happen at any time, where our current vacuum tunnels into a more stable state, rewriting the laws of physics and destroying everything in an instant. But what if that's already happened, once? What if the Big Bang wasn't the birth of space-time, but the aftermath of such a decay? The cosmic constant we're measuring now isn't just a guess in this case, it's survivor data, the faint hum that was left over from a universe that broke apart and put itself back together again to become the one we live in now. Theories about multiple universes offer another reason. There could be an endless number of universes, and each would have a different vacuum energy. Most of them would either grow too fast for stars to form or shrink too fast for anything to grow. We are in a very small bubble where the cosmic constant is low enough to support complexity. This isn't by design. We couldn't be in any of the other bubbles. But even this anthropic reasoning doesn't explain why the number is so precisely small and not just zero. That level of fine-tuning suggests a process, some cosmic editing, took place. A filter, a crash, a reset. Something that didn't finish perfectly. The cosmological constant might just be a glitch. Something left over from a bad change between states of reality. A number that should have been rounded to 2 decimal places but never was. This strange lasting value, this 10 to 320 whisper in the void, might be one of the few straight signs that our universe has a past that it can't fully hide. The fine-tuning enigma. Was it tweaked after a crash? When we look at the big picture of how our universe is put together, one thing becomes very clear. It looks like the universe is set up for life. The range of the scientific constants in nature is too small for words. They include things like the force of gravity and the charge of an electron. If you change even one of them slightly, the world as we know it will end. There are no stars. Atoms don't stick together. Life never comes out. This mystery is known as the fine-tuning problem, and it's one of the most compelling clues that something deeper, possibly even broken, might be hiding in the backdrop of our cosmic origin. Let's run through just a few numbers. If the strength of the strong nuclear force were slightly weaker, protons and neutrons wouldn't bind, and atoms beyond hydrogen wouldn't exist. No carbon, no oxygen, no life. If it were stronger, stars would burn through their fuel too fast. If the cosmological constant were even slightly larger, the universe would have expanded too quickly for matter to clump into galaxies. If gravity were weaker by even a fraction, everything would drift apart. If it was stronger, the universe would collapse. And this isn't just about one constant. It's dozens, all perfectly balanced in what appears to be a cosmic code, too perfect to ignore. Traditional explanations fall into three camps. One says it's coincidence, we just got lucky. Another says it's design, a cosmic architect set the dials. The third is the multiverse. If there are infinite universes with different constants, we naturally find ourselves in the rare one where the math works. But what if there's a fourth choice? What if the world crashed and then changed? Imagine a very fragile universe from the past. There are constants all over the place. Not any stars, no organization, and no balance. It spins out of control, falls apart, and starts a bounce, a reboot, or a vacuum transfer. It learns this time though. Changed values, stable ones, are still present in the new world. Static elements that help with complexity. What if fine-tuning is the result of mistakes made by the universe? This fits with views like cosmological natural selection, which says that the way worlds change is not through DNA, but through physics. Those that create stable settings stay alive by using black holes or bounces to create new worlds. Those who don't go away. After a while, universes are set up in a way that helps things like stars, galaxies, and finally minds stay alive. The world is seen as a self-correcting system in a different form of this theory. When the universe goes through a major breakdown, like a vacuum decay or a brain collision, it comes back with corrections. Not just any ones, but ones that are based on what went wrong with the last version. Changes are made to the factors. Not exactly, but just enough to keep things from falling apart again. Could this be the reason why our world only just seems to work? It's not perfect. Not as fast as it could be. Not great, but good enough. Like putting together a car from old parts. It shakes, but it moves. This view changes the idea of fine-tuning from a mysterious accident to a result that can be tracked, a sign that something went wrong earlier, that the constants we see now weren't built into the universe from the beginning, but were changed, possibly in a rough way, after something went wrong. This could also explain the strange events that happen to people. Why do the rules of physics make it possible for viewers like us to appear? It's possible that they didn't do it in the last round. There may have been times in the past when the world was close to becoming aware, but it never quite made it. That could also tie into simulation-style thinking. If a previous reality hit a wall, became unstable, too chaotic, or too lifeless, it might have been rebooted with better parameters, recompiled, rebalanced, tweaked to avoid another crash. Do wormholes link our universe to an older one? Wormholes are a common theme in science fiction for a long time. They are a way to skip through space-time or join two very different parts of the world. But wormholes are real in the field of theoretical physics. They make sense theoretically, and some scientists think they could be more than just ways to travel through space. They might be links between worlds, maybe even one that came before ours. A wormhole, or Einstein-Rosen bridge, is a solution to Einstein's equations of general relativity. It describes a tunnel-like structure that connects 2 points in space-time. These aren't just science fair models, they're baked into the math of gravity itself. Under the right conditions, they could link not only 2 distant galaxies, but two entirely different cosmic regions. Some versions of the theory suggest that wormholes might not only link different parts of our universe, but entirely separate universes. In certain multiverse or brain cosmology models, universes aren't isolated islands. They're more like sheets or bubbles that exist in higher dimensional space, called the bulk. Wormholes could pierce through this bulk, connecting one universe to another. There was a big crunch, a vacuum collapse, or a black hole burst, and the universe was dying. What if a wormhole opened and connected that universe to a new one that was growing? The remains of that old universe could have broken through and helped ours grow. Some physicists even say that black holes are wormholes, which means they lead not to death but to new worlds. Things don't just disappear when they fall into a black hole. It goes through a wormhole and comes out the other side in a different part of space-time. That brand new site, a whole new world, it could be ours. If this is true, wormholes aren't just oddities. They're umbilical cords linking the end of one reality to the beginning of another. Wormholes, if they exist, might still be able to connect us to the past, to the broken shell of a once great universe. To compare, skeletons tell us about life that lived a long time ago, and wormholes might bring information from another world into ours. Waves of radiation, gravity, or quantum changes could pass through, making strange things that we might be able to see if we knew where to look. As an example, think about the cold spots in the radiation from the sun. Could one of them be a place where the ghost of another world touched ours? Could wormholes be the cause of patterns that don't make sense, or changes in the direction of things in deep space? Of course, this is still just an idea. For wormholes to stay open, they would need strange matter, which is stuff that has a negative energy density. Without it, they fall apart very quickly. We haven't found this kind of matter yet, but quantum field theory says it could exist in some situations, like the Casimir effect. But the universe may have already found and built wormholes, so we don't have to. As the quantum foam was being formed, it may have had natural wormholes during its early stages, either during the chaotic flash of the Big Bang or right before it. And if even one of them links us to a past reality, another world that died so that ours could exist, then we're not alone. We are linked by holes in space-time and consciousness that make up a chain. We might never walk through one. If wormholes do connect worlds, though, they may be the only way we can reach the past. Negative energy, the smoking gun of a lost world. Kinetic, potential, and thermal energy are the most common types of energy that most people know about. But negative energy is a strange kind that doesn't get much attention in the strange fields of quantum physics and astronomy. It's not made-up science fiction. It's true. Some scientists think it might be the last sign of a world that existed before ours. A silent sign of an event in space that we were not meant to see. To be clear, negative energy isn't just less than zero in the everyday sense. It's not cold air or missing fuel. It's a physical property of space itself, predicted by quantum field theory, necessary in many exotic models of the universe, and utterly bizarre. In quantum mechanics, the vacuum isn't truly empty. It bubbles with particle-antiparticle pairs that briefly appear, borrow energy from the void, and disappear again. This constant activity gives rise to vacuum fluctuations, and in certain configurations, like between two metal plates in the Casimir effect, these fluctuations can be manipulated to produce a region with negative energy density. Theoretical models of wormholes, warp drives, and even quantum gravity require negative energy to make the math work. In many cases, it's the glue that keeps space-time from tearing apart, or the fuel that bends it into impossible shapes. What if the subtle, hard-to-grasp negative energy we see in the world right now isn't just a quantum curiosity? What if it's still there? What if it's something from a different universe? Imagine that the fall of a previous universe sets off a quantum event, such as a bounce, a tunneling process, or a change in dimensions. Even though the old world ends, its parts don't go away. It makes a mark. Whirling threads are left behind in the quantum vacuum. Those threads are still here, but they can't be seen or counted because they are part of the universe's energy environment. Negative energy could be the smoking gun. It's a feature that doesn't make sense in normal models, but makes perfect sense when seen as old code from a deeper, older cosmic system. Some physicists have proposed that dark energy, the mysterious force driving the accelerated expansion of the universe, might actually be connected to this. Maybe what we call dark energy is really an echo of negative energy left from a vacuum decay or a dimensional fold. Maybe the universe didn't start from zero, but from a balance sheet with leftover debt. Other models, like those in string theory or loop quantum cosmology, suggest that negative energy may stabilize the bounce between cycles of the universe. In this view, negative energy is what allows one universe to fold in on itself, condense, and then expand again, providing a mechanism that makes cyclic universes possible. Some researchers even speculate that black holes might be gateways to regions with negative energy, and that the Hawking radiation they emit could, in part, carry information about this deeper state. In other words, black holes might not destroy information, they might reveal it, whispering about the structure of a past universe encoded in their evaporation patterns. At this point, negative energy is still only a theory. It's like a mathematical shadow that keeps showing up in astronomy, gravity, and quantum physics. The result may already be built into the shape and fate of the world we live in, even though we haven't seen it directly. We might be able to get to the world before the Big Bang if we can prove it, if we can measure it, catch it, or recreate it. A place where energy didn't start at zero and was full of scars, oddities, and rules left over from a world that was no longer being made. Vacuum decay. Could the universe be ending now? Think about this. A small bubble appears in space, maybe far away or right next to you. It can't be seen, can't be stopped, and is growing faster than light. It hurts more than just planets and stars. It changes the rules of physics. Things like matter, energy, space, and time stop being the way they are. The worst part? You wouldn't have seen it coming. It's one of the scariest things that can happen in current science. This process is known as vacuum decay, and it could be going on right now. First, we need to talk about the quantum void in order to understand this dream wrapped in an equation. Quark field theory says that empty space is not really empty. It's a boiling mix of virtual fields, particles, and changes in energy. Even in a vacuum, the Higgs field, electromagnetic fields, and gravity fields are all always moving back and forth. It's more important than you think that this vacuum's energy state is stable. From what we can tell, our universe is in a metastable vacuum. So it's not the lowest energy state possible. It's just stuck in a local minimum, like a marble sitting in a small valley while a deeper valley is nearby. Metastable states can stay around for a very long time most of the time. They can get through the energy barrier and into that lower state, though, if certain things happen. When is that going to happen? It takes place in a space. In this case, all of a sudden, a bubble of true vacuum shows up. The basic rules of physics are not the same inside the bubble. Things that don't change, like the speed of light, the charge of an electron, and the force of gravity, could all change. It would not work with chemistry as we know it. Atoms might not even come together. As the vacuum we live in breaks down into a more solid one, everything in our world stops being compatible with life. We would never see it come closer because the bubble grows at the speed of light. There wouldn't be any notice. There are no alarms. There was no light flash. Your particles are doing what they've always done 1 second, and then they're gone the next. In 2012, measurements of the Higgs boson at CERN revealed that its mass, around 125 GeV, combined with the mass of the top quark, implies that the Higgs field's vacuum potential could indeed be metastable. The precise numbers depend on measurements with tiny uncertainties, but we're right on the edge between stability and instability. Some calculations suggest our vacuum could last trillions of years. Others hint at decay happening sooner. It could happen through a quantum fluctuation, a rare random event where the energy density spikes just enough to push the Higgs field over the edge. It could also occur due to cosmic rays, black hole evaporation, or even through human-made experiments like particle accelerators, though current science says that's unlikely. Once the bubble forms, the transformation is absolute. Space is redefined. Time itself may take on new properties. Dimensions might be rearranged or collapsed. Even the notion of causality, the idea that one thing leads to another, could cease to make sense. The universe, as we know it, becomes a footnote in a different kind of physics. If vacuum decay truly does occur, it might not just be an end. It could be a transition, a reinitialization, the death of one rulebook and the birth of another. Inside the expanding bubble, a new universe might be born, governed by different physics. Our universe might itself be the product of a past vacuum decay. We might be living inside such a bubble already. There are ideas like the multiverse and endless inflation that connect this possibility. In these ideas, different parts of space fall into different vacuum states. In this world, each bubble is a universe, and the process by which universes grow is called vacuum decay. So the end of our world could mean the start of a new one. That could have happened already. Maybe the Big Bang was the collapse of a vacuum in a parent universe. Then, what we think of as the beginning of time was really just the front of an expanding vacuum bubble-changing reality as it went. In this model, the multiverse doesn't grow like a branching tree. It boils like water, with new universes bubbling up randomly in a chaotic sea of vacuum states. Ours is just one bubble, expanding outward from a moment of collapse. This theory also raises philosophical questions. If a vacuum decay is inevitable and silent, then are we living on borrowed time? Is there any point in searching for meaning, building civilizations, or chasing knowledge if everything can vanish without notice? We are a part of a life process if vacuum decay is a part of nature's largest system. The world isn't a static wonder. It's part of a cycle of change that goes on all the time. There is both creation and destruction, rise and fall. We may not last forever, but because we are a phase, we have value, a state, a one-of-a-kind arrangement in the big experiment of life. Chances are still important. Most models say that the half-life of our vacuum is many orders of magnitude longer than how old the universe is now. There is a very, very small chance that vacuum decay will happen in our galaxy anytime soon, even if it is real. Dark energy and the Big Rip, prelude to a new Big Bang. The universe is being pulled apart by a force that is moving quickly and not slowly. There is something in the universe that we don't fully understand called dark energy. It makes up about 70% of the universe and speeds up the growth of space. But what happens if dark energy doesn't just keep pushing, but pushes too far? What if it rips everything apart, from the largest galaxies to the smallest atoms? This isn't just theoretical. It's a hypothesis called the Big Rip. And it may not only end the universe, but also set the stage for something new. To understand the Big Rip, we have to go back to what we know about cosmic expansion. Ever since Edwin Hubble discovered that galaxies are flying away from each other, we've understood that the universe is getting bigger. But in the late 1990s, two independent teams of astronomers studying distant supernovae made a startling discovery. The expansion is speeding up. Gravity, the force pulling matter together, should have been slowing the expansion over time. Instead, something unknown was overpowering gravity on cosmic scales, stretching the fabric of space more and more with each passing moment. That unknown something was named dark energy, a term as mysterious as the force itself. Dark energy doesn't behave like normal matter or radiation. It doesn't dilute as the universe expands. Instead, it acts like a constant energy density of space, or in some models, like a slowly changing field. The more space there is, the more dark energy there is, because it's tied to space itself. If dark energy remains constant, like Einstein's cosmological constant, the universe will expand forever, galaxies will drift apart, and over trillions of years, stars will burn out. That's already strange enough. But if dark energy gets stronger over time, we're in far deeper trouble. The energy level doesn't stay the same in this case, which cosmologists call phantom energy. It gets bigger. It starts to be stronger than all the other forces in the universe because it is pushing space apart. It's not just gravity. Everything. In the beginning, it pulls galaxies apart by stretching them. At that point, it breaks up solar systems, freeing planets from their stars. Next, it pulls apart stars, planets, atoms, and finally the universe itself. This is the Big Rip, a theoretical cosmic apocalypse where the expansion becomes infinite in a finite amount of time. The timeline depends on how dark energy behaves. In a 2003 paper by Robert Caldwell and colleagues, they estimated that if phantom energy exists, the Big Rip could occur in as little as 22 billion years. Long after our sun dies, yes, but cosmically speaking, it's not that far off. The process unfolds in reverse order of binding forces. First, the largest structures are torn apart, galaxy clusters and galactic filaments, then individual galaxies, then star systems, then the stars themselves. Eventually, atoms are stretched until electrons are unbound from nuclei and molecules cease to exist. In the last few seconds, even space and time are warped so much that they lose their meaning. It's not like the world ends. It tears itself apart into math nonsense. Could this horrible death spiral, though, be the start of something? The Big Rip might be a point of infinite growth, just like black holes collapse matter into singularities, which are places of infinite density. In both cases, the world reaches a point where the laws of physics we know no longer apply. Another possibility is that what comes next is not destruction, but a change in phase. Consider about this. The universe grows until all structures are pushed to their limits, all the way down to the level of quantum fields. This break could cause a vacuum transition, in which the fabric of space falls apart into a new, lower energy shape. That would essentially start over with the rules of physics, putting the universe back into a state of nothingness. This idea fits with some forms of quantum gravity and string theory, which say that space-time isn't a single thing, but is made up of separate pieces. If those units are stretched or vibrated past their limits, they may rearrange themselves into new shapes. A new set of dimensions, a new Higgs field, and a whole new world. In that sense, the Big Rip wouldn't be an end. It would be a puncture into the next universe, a ripping of the veil that reveals a deeper layer underneath. Some ideas say that the Big Rip could be a start for a cycle. If the universe is always expanding and tearing itself apart, the tear could create bubble universes, which are stable areas where the growth starts over, particles come back together, and space-time starts to put itself back together again. Each bubble could be a new Big Bang, with its own physics, particles, and rules. In that setting, the Big Rip turns into a birthing event, a cosmic body that gives birth to reality over and over again, though each time with small changes. Some bubbles burst right away. Some make huge, complicated buildings, like the ones we have. Some physicists argue that the beginning of our universe already looked like the end of another. The ultra-hot, high-density conditions of the Big Bang mirror what happens near a rip or collapse. Maybe we're already living in a universe that formed after a prior Big Rip. Maybe this expansion is just the latest ripple in an endless sea of tears and births. Even the mathematical models that describe inflation, the rapid expansion after the Big Bang, share features with phantom energy. It's possible that ripping and inflating are part of the same engine, the same fire, the same cycle. The Big Rip is just one scenario among many. Current observations don't yet confirm that dark energy is increasing. Most evidence still points to a cosmological constant, but the margin of error leaves the door open. The future of the universe depends on one decimal point in one equation. Holographic universes and dimensional leftovers. What if the world you live in, see and touch, isn't even close to being the whole picture? What if everything around you, from worlds spinning around to your own hand, is just a projection? What if everything around you is just a shadow cast by a deeper, more basic layer of reality? It's a growing and serious hypothesis in theoretical physics called the holographic principle, and it may explain not only the strange behavior of black holes and quantum fields, but also offer clues about dimensions that existed before our universe began. In the search for what the Big Bang truly was, this principle might point to something extraordinary. Our universe is the surface residue of a higher dimensional process. And that means something older, deeper, and more complex might be hidden beneath the surface. Physicists have known for decades that when matter falls into a black hole, the information about that matter doesn't vanish into the singularity. Instead, it seems to be encoded on the event horizon, the two-dimensional boundary that surrounds the black hole. This was a shock. We're used to thinking that more volume means more information, but here it was. The surface told the story, not the inside. What that meant was shocking. In other words, it meant that maybe all the data needed to explain a three-dimensional space could be kept in two dimensions. It's possible that the world works like a hologram, where a 2D picture can make a 3D image. At that time, physicists Gerard 't Hooft and later Leonard Susskind came up with a crazy idea. Maybe the whole world is made of holograms. Maybe everything we think we see in 3D is actually stored on a cosmic border, a 2D screen that is very far away from our view. This is the holographic principle, and it gets even stranger when paired with ADS-CFT correspondence, a powerful mathematical discovery by physicist Juan Maldacena. In this model, a universe with gravity in a five-dimensional space, anti-de Sitter space or ADS, can be equivalent to a universe without gravity in 4 dimensions, conformal field theory or CFT. The bulk and the boundary match perfectly. One describes the other. We don't live in anti-de Sitter space, but the math works so beautifully that many believe a similar correspondence might apply to our own de Sitter-like universe. That raises the possibility that our cosmos is a projected version of something more fundamental, something existing in more dimensions than we can directly perceive. If you believe some string theories, there are 10 or 11 dimensions, but we can only see 3 of them, space and time. What about the rest? They're curled up and packed together at Planck lengths, so we can't see them. They may have been active in the early universe, though. They might not curl up on their own, though. What if they were leftovers, the broken frames of a previous universe? In this view, our Big Bang wasn't just a burst of heat and particles. It was a dimensional transition. Something more complex collapsed, imploded, or transitioned. And what we experience as our universe is just the 2D boundary residue of that higher dimensional entity. The vast symmetry of whatever existed before broke down, and in its wake, our reality formed like a cosmic scar. It might be like a dimensional fossil, like a footprint in rock shows us the shape of an extinct animal. Our 3-dimensional world might hold geometric clues of the more complex shape it once had. Could things like dark energy, dark matter, or quantum fluctuations really be shadows of physics that happens in other dimensions? Could the black holes in our universe be holes in the 3D cloth that let information from bulk space in higher dimensions leak out? Could some strange things in space, like the CMB cold spot or the axis of evil, be projection objects that show our universe is not the whole story? Time appears on its own in some hologram forms. It comes from patterns of interaction on the edge of the universe. In other words, development, order, and causality are not built into the base layer of reality. They are made by the projection. The greater truth may be eternal, constant, and impossible to imagine. This point of view fits in with ideas about cosmic inflation as well. It's possible that the universe grew so quickly, not because of an internal field, but because it was emerging from a boundary surface. An explosion of projected data, like how a balloon takes shape by having a pattern pressed onto it. If it's true, the Big Bang wasn't the start of anything. It was an event for drawing. It's possible that our world was calculated not digitally, but physically. It wasn't worked out from zero. It was worked out from what was left over. What about those extra dimensions then? Can we find them? Some models say that gravitational waves might be able to travel through extra dimensions and leave behind fingerprints that are weak but clear. Some people think that particle accelerators might make very small, unstable particles that get lost in space of higher dimensions. We haven't found any strong proof yet, but as tools get better, the hunt goes on. We may also find clues in the structure of space-time itself. The universe is flat, but not perfectly. Its curvature, if measured with enough precision, could hint at a shadow shape, the outline of something deeper. Just as a crumpled paper casts a strange shadow, our universe may reflect the folds and warps of a hidden dimensional reality. If our universe is holographic, then the real universe isn't even here. It's out there, on the boundary. What we experience is an illusion of depth, rendered so convincingly by the laws of physics that we believe it's solid. Many physicists now argue that information is the bedrock of everything. It's not that matter gives rise to data, it's that data gives rise to matter. From this perspective, our entire universe is a meaningful arrangement of information, structured by boundary conditions we may never fully perceive. Quantum Darwinism, survival of the realist. Quantum physics says that particles can be in more than one place at the same time. Cats can be alive or dead. Whole systems can live in a fog of options until they are measured by something or someone. It seems strange and goes against common sense, and an experiment has proven it. But if that's true, why doesn't the world look that way? Why do we experience a crisp, definite reality? One version of events, one timeline, one solid cat. Enter quantum Darwinism, a bold and rapidly emerging theory that might just explain not only the classical world we see, but the universe itself. And more provocatively, it might hint that we live in a version of reality that survived, while countless others didn't. At the heart of the mystery is the measurement problem in quantum mechanics. In the standard view, a system exists in a superposition of all possible states until it's observed. Observation collapses the wave function, selecting one outcome from many. For decades, physicists couldn't agree, until a new idea emerged in the 1980s and 1990s, decoherence. This theory showed that quantum systems don't need conscious observers to collapse. They simply need to interact with their environment. As a particle bumps into air molecules, photons, or anything else, its wave function becomes entangled with them, rapidly selecting a state in a process too fast and complex for us to reverse. But decoherence by itself doesn't explain why we see the classical world the way we do. We can use quantum Darwinism to explain this. This theory, which was put forward by scientist Wojciech Zurek, goes beyond decoherence with a strong analogy. The choosing of reality works like evolution. A quantum system has a huge number of states that start out in superposition, but only a few of them are strong, stable, and able to change the world around them. Just as evolution favors traits that help organisms survive and reproduce, quantum Darwinism favors quantum states that can be copied redundantly and persistently across the environment. These states survive. The rest die off, unmeasured, unmanifested, unremembered. To put it another way, only the most stable forms of reality become real. That's what you see when you open your eyes. This choice doesn't need to be made on purpose. It's all mechanical. It's just the way things work with data. A state is agreed upon by everyone when it is repeated many times, like when a tree's position reflects light into millions of photons. The surroundings makes the tree's quantum state stronger, so everyone who sees it sees the same thing. What does this mean for everything? It means that truth isn't just seen, it's controlled. It doesn't happen by chance. Selection pressure makes it happen. That process could have started before there was life, before there were atoms, or even before time as we know it. Some scientists say that quantum Darwinism was at work in the early world and shaped how space-time evolved. Natural selection worked on the first quantum fog, which was a cloud of uncertain odds. Some states were the only ones that were strong enough to spread. Only some combinations made it to the end of the cosmic era. In this view, the Big Bang wasn't just an explosion of matter. It was the collapse of superposed realities into a stable branch. Our universe isn't the only one that could have existed. It's just the one that made it through the quantum bottleneck. Think about that. The fundamental constants, the speed of light, Planck's constant, the masses of particles, might not be random or designed. They might be the traits that allowed this branch of the universal wave function to endure. The rest collapsed into decoherent fragments, lost before reality even began. This idea has huge effects on the cosmos, awareness, and the study of the universe. All possible worlds are said to be in quantum superposition in the multiverse view, but not all of them are chosen. Quantum Darwinism offers a reason for our observation. It's the one that managed to copy itself best in its own surroundings. As observers, we amplify certain patterns. We interact with the universe, record its behavior, and reinforce specific branches of its evolution. The rise of sentient beings may not be an accident, it may be a feedback loop. Intelligence selects for stable reality, and stable reality enables intelligence. This might even help show how time moves. The universe chooses states that are easier to copy across the world, which makes entropy rise. Time moves in a way that isn't just mechanical, it's also evolving. The past is summed up by the event that left the clearest marks. The future is wide open, but only the ways that don't give up will live. It leaves us with a universe that is real, but only because it survived. A reality filtered not by consciousness alone, but by quantum stability. A cosmos where only the realist versions of events rise to the top and the rest fade into quantum oblivion. Information never dies. Could we reconstruct a past universe? These days, lost doesn't mean the same thing it used to. The information is still there after something burns, crashes, or goes into a black hole. No, we may never get it back in the same form. Not really. Not always. That idea changed the way physics is done today. For if it's true, it brings up a big new question. Could we one day build a universe that existed before ours? Information conservation is one of the most important ideas to come up in theoretical physics in the last 40 years. The idea of entropy taught us in traditional thermodynamics that as order breaks down, systems become less predictable, and data seems to fade. Quantum physics, on the other hand, said that even though order breaks down, the information is still stored in the system. It's just spread out, tangled up, not seen. According to Einstein's general relativity, black holes are regions of space-time where gravity becomes so intense that nothing, not even light, can escape. Traditionally, it was thought that anything that fell in was lost forever. But in the 1970s, Stephen Hawking discovered that black holes aren't entirely black. They slowly evaporate, radiating energy in the form of Hawking radiation. Hawking radiation appears random. If a black hole eventually evaporates and all that comes out is noise, then whatever fell into it, stars, matter, data, seems to vanish without a trace. That would violate one of the fundamental rules of quantum physics, unitarity, which states that information must be preserved. This led to the famous black hole information paradox, a debate that raged for decades. But mounting theoretical and mathematical work, especially from string theory and holography, has pointed toward an astonishing resolution. The information isn't destroyed, it's stored on the event horizon. In line with the holographic principle, this means that data recorded on the edges of a volume of space can explain all the information that is contained within it. Not only can a black hole keep everything it eats, but the world may work the same way. The Big Bang didn't erase the past if the universe keeps information safe at all times, even when it collapses and hits a singularity. It squished it, it made it secret. In theory, this means that the world that came before ours is still out there, though it may only be in bits and pieces. Since our universe is the first one, how could we even begin to build another one? We'd need to find the info first. There are some scientists who think that quantum entanglement, which connects particles across space and time, might hold clues about a past cosmic cycle. There might still be bits of information from a previous universe in the universe we see now, even if it fell or changed into something else. There may be strange features in the cosmic microwave background, such as cold spots or breaks in the symmetry that don't make sense, that could hold clues about past events. There may also be scars from another world in the shape and curvature of space itself. The second step is to figure out how the physics work. It's possible that the universe's scientific constants, particle families, and symmetries are not chosen at chance. there are scientists who think that these values might have been passed down from an earlier universe, like a quantum DNA code. If we could find these factors in the past, we might be able to figure out how the world was built in the past. Last but not least is modeling. This idea is no longer just a fantasy thanks to quantum computing. If we can figure out how knowledge stays alive during cosmic changes, we might be able to model the early universe, not just the Big Bang, but also the universe that came before it. We might be able to see the last moments of a dying world whose memory still lives on in ours, like putting together the pieces of an old city from its many wrecks. If black holes conserve information, and if our universe was born from a collapsing region, perhaps even the interior of a black hole in another cosmos, then everything we are is already part of a memory stream. Our atoms, our laws, even our timeline. Some people even think that the universe sends information instead of just encoding it in some kind of conformal circular cosmology. In other words, what happened before actually shaped what happened after. In other words, there is a framework that lasts through all the rebirths. What this means is shocking. This not only makes us question what we think about death being final, but it also makes it hard to tell the difference between creation and continuation. The Big Bang stops being a fireworks show and starts being a bridge, a way to squeeze one world into another. The evidence trail. Can we detect what came before? For all the elegance of theories and beauty of speculation, science ultimately demands one thing: evidence. No matter how poetic or mathematically precise our ideas may be, they remain shadows until something physical, measurable, confirms them. And when it comes to the question of whether there was a universe, or many, before the Big Bang, the hunt for such evidence is no longer a fantasy. It's underway. Quietly. Meticulously. And in some corners of physics, it's beginning to yield whispers from the dark. Cosmologists and theoretical physicists are now actively investigating whether the early universe carries imprints of something older, clues that may have survived the firestorm of the Big Bang itself. We may not be able to observe anything beyond the Planck time directly, but that doesn't mean nothing was left behind. Like ashes under fresh paint, anomalies in the structure of the universe might be remnants of a former reality. The cosmic microwave background, which is the glow left over from the Big Bang, is one of the best places to look. This almost uniform bath of ancient light was found in 1965. It has tiny changes in temperature that are the building blocks of all future galaxies and the framework of the universe. It is likely that these changes will happen at random and be the same in all directions. They're not, though. Alignments are not too obvious. That's not normal. Cold spots for no reason. The axis of evil is one of the most well-known. It is a strange arrangement of low multipoles in the microwave background that doesn't make sense from a cosmic point of view. Some people think it's just a random oddity. Some people think it might be the mark of a universe that existed before ours. Then there's the possibility of gravitational echoes, faint ripples in space-time from cataclysmic events. Gravitational waves, first detected in 2015, have given us a new sense for the universe. But current detectors only pick up high-energy events like black hole mergers. If a previous universe collapsed or transitioned into ours, it might have left behind low-frequency gravitational waves that still ripple through space today. These primordial waves, if found, could tell us not just about the Big Bang, but about what happened before it. Efforts are already underway. Projects like LISA, the Laser Interferometer Space Antenna, and CMBS-4 aim to measure the cosmos with precision never before achieved. They could detect faint gravitational noise or subtle polarization patterns in the cosmic microwave background, specifically a type called B-modes, which might carry the signature of pre-Big Bang dynamics. In this context, even the lack of expected data could be revealing. If we find something that standard inflationary models cannot explain, the door opens wider for cyclical cosmology, bouncing universes, or even quantum gravity effects from epochs we thought forever sealed. Another trail of evidence may lie in particle physics. The universe as we know it is governed by a set of constants, values that seem fine-tuned for life, balance, and complexity. But what if that fine-tuning is a side effect of inheritance? What if these constants were not set at random, but passed down, like genetic traits, from a previous state of the cosmos? The nearly perfect symmetry breaking between matter and antimatter, the slight imbalance that allowed matter to dominate instead of being annihilated, these things may have roots deeper than the Big Bang itself. The very existence of matter might be a surviving feature from a prior universe's structure. Some physicists even speculate that dark matter and dark energy, the two most dominant and least understood components of the universe, might themselves be residuals, forms of energy or particles that don't belong to our phase of the cosmos, but drifted in from another. If dark matter doesn't interact with light and only responds gravitationally, could it be a surviving shadow from another realm? A fossil from a deeper past? The topology of the universe, the way space itself is curved and connected, could also contain buried stories. If the universe has an unusual shape or twist, that might not be due to chance. It could be an imprint of the geometry of a previous universe. Think of it like a scar on skin. You can't see what caused it, but you know something did. There's also the approach of information theory. If information is conserved, as many believe it must be, even through black holes, even through vacuum transitions, then somewhere in the quantum entanglement patterns of our universe, the past is still there. Not in the way a book records history, but more like a pattern encrypted into the structure of reality. It's possible that future advances in quantum computing and quantum field theory may allow us to decode this pattern, to trace entanglement backwards, to extract an ancestral story. Of course, skeptics argue that these are just curiosities, that the anomalies in the CMB are artifacts of our instruments, our location, or our statistical methods, that the fine-tuning of constants can be explained by selection bias. We see a balanced universe because only in such a place can observers like us exist. But even these skeptical explanations concede a point. They admit that something unusual is going on. Whether it's luck, necessity, or legacy, the universe seems less random the deeper we look. And in all of this, there's a strange emotional undertone. For the first time, the question, what came before the Big Bang, isn't just philosophical, it's testable. The boundary between science and speculation has shifted. We no longer have to accept that the past is unknowable just because it's unreachable. There may be fossils in the sky, ripples in the dark, geometry that remembers. Cosmic memory. Is the universe remembering a past life? The way we remember things is a biological process stored in neurons and changed by time. What if memory is deeper than that, though? Not in the brain, but in the very structure of reality. If the world doesn't just grow and change, what if it remembers? This is the idea behind cosmic memory, a speculative but increasingly compelling notion that the universe may carry traces of what came before it. Not figurative traces, not poetic echoes, but real, physical, quantum-level memory encoded in the fundamental architecture of existence. In modern physics, information isn't just something humans interpret. It's a fundamental property of nature. Particles aren't defined solely by position and mass, but also by the information they carry. And one of the most provocative developments in quantum theory is the realization that information may be indestructible. Even when matter is annihilated, even when black holes evaporate, the information embedded in those systems still exists, somehow, somewhere. If information persists no matter what, even through a cosmic collapse or transition, then the universe itself could be remembering what came before. One route through which this memory might operate is quantum entanglement. Entanglement links particles together such that the state of one instantly determines the state of another, no matter how far apart they are. But some researchers are beginning to ask, what if entanglement doesn't just cross space, but time? That is, what if quantum coupling links not only particles, but also epochs? Imagine that the end of one world is connected to the beginning of another. It's possible that that entanglement wasn't broken during a cosmic bounce or a vacuum decay event. It was carried through. Some of the states that formed in the early universe might have something to do with the last breath of the previous universe. Could the early density changes, the low entropy of the Big Bang, and the exact values of physical constants all be traits that were passed down? If that's the case, memory and science both shape the world we live in. In some interpretations of quantum mechanics, especially those rooted in the many worlds interpretation, reality doesn't split because of observation, but because of decoherence. And decoherence leaves behind patterns, like footprints in quantum foam. The classical world we experience may be one version of events among many, but it is also the version that has accumulated the most reinforcement. That extra help is a memory in and of itself. Through endless interactions and repetitions, the universe knows the routes it has taken and keeps going in the same ones. This brings up another thought. The way structure stays the same. The world has an amazing ability to organize things over and over again, from planets to atoms to genetic codes. Patterns keep happening. Structures come back. Even when things are completely different, processes tend to be set up in ways that are familiar. Why? Is it just luck, or is there something more going on? In loop quantum cosmology, where space is not smooth but granular, the universe doesn't start from a singularity, but from a bounce, compressed to a finite size, then rebounding. The prior universe may leave behind more than a bang. It may leave behind imprints in the topology of space, encoded in the very way quantum loops are arranged. These patterns would influence the unfolding of the next universe, not through causality, but through continuity, the speed of light, Planck's constant, the strength of gravity. These values define the shape of reality, yet no law of physics determines what they must be. They could be anything, but they aren't. They're precise, balanced, and seemingly tuned for complexity. Why do you think these aren't random? So what if these ideals are old ones? Constants may be data that stays the same through bounces, crashes, and rebirths, similar to how memories are stored during cosmic changes. If each past universe left behind its physical preferences, then the current universe may have the quantum memories of past worlds. Some scientists also think about the idea of topological memory, which says that the universe's overall shape might still have marks or folds from an earlier universe. The universe we live in looks flat, but there is a small curve to it. That curve might not be a quirk. It could be a mathematical memory of how the universe before this one bent and collapsed. What if the mind is the tool that memories are made of? Many spiritual and philosophical systems see awareness not as something that just happens, but as something that is built into the very structure of the world. Some versions of panpsychism and integrated information theory say that everything, from atoms to galaxies, is aware of itself. From this point of view, awareness isn't just something that happens in the world. There is a channel, something that the universe uses to remember itself. Could it be that when a universe collapses, its structures, both physical and conscious, are drawn into a singularity of memory? And when the next universe begins, that data isn't destroyed, but redistributed, re-expressed in subtle, invisible ways? Why do stories from different times and cultures talk about rounds of death and rebirth? Why do a lot of old beliefs talk about cosmic memory, the Akashic records, and historical knowledge that has been passed down through space and time? It's possible that those stories weren't just metaphors. They could have been natural understandings of something real, like the fact that the universe doesn't forget. End times of the previous cosmos, a tale lost to time. Every start hints at an end that came before. And if our universe came from something else, like a vacuum transition, a cosmic collapse, or a fold in space and time, then what was there before us had its own long story, structure, and form of time. But it had to die in the end too. This is the tale of a previous cosmos, not remembered in stories, but perhaps buried in our equations, not told by witnesses, but hinted at in the silence between the stars. Visualize a world that is expanding, thriving, and incredibly complicated. It has its own air, stars, and even living things. its own physics, which could be very similar or very different. It is ordered, though, so it will finally be overrun by chaos. The second law of thermodynamics says that things tend to get out of order. This law refers to all known areas of physics, and the universe can't get away from this tide, no matter how bright or big it is. The most well-known is the heat death. Over trillions upon trillions of years, stars burn out. Matter decays. Black holes slowly evaporate through Hawking radiation. Temperature differences flatten. The universe becomes cold, dark, and uneventful. No more light, no more heat. Just a thin fog of particles drifting in endless space. Time becomes meaningless because nothing changes. Another possibility is the Big Crunch. In this scenario, expansion halts and reverses. Galaxies begin to fall back toward one another. The universe contracts, temperatures rise, structures collapse. Eventually, everything is compressed into an unimaginably dense state, a singularity, a place where the rules of physics break down, where time itself ceases to function, and then, perhaps a bounce, a new beginning, a phoenix moment. What if that previous universe underwent vacuum decay, collapsing into a lower energy state, erasing all that came before in a wave of annihilation? Or perhaps it passed through a phase transition, a symmetry shift that shattered its existing laws and birthed ours. In these scenarios, the prior cosmos didn't die by fading. It transformed violently, leaving only fragments of itself embedded in the vacuum state we now occupy. Entire clusters of galaxies ripped apart, stars exploding without context, atomic structures breaking down as constants shifted, space collapsing, time stretching or snapping. Imagine a world where electrons no longer orbit nuclei, where gravity no longer attracts, where matter itself forgets how to exist. That is what a dying universe looks like, not just visually but structurally, the way a scar on the land reveals where a river once flowed. Certain anomalies in our universe might mark the final breath of its predecessor. The peculiar cold spot in the cosmic microwave background, the strange alignment of large-scale structures, the arrow of time, and its mysterious origin in low entropy conditions at the Big Bang. What made the world start out in such a strange and ordered way? It could be because it got that order from the last frame of a world that didn't end in chaos, but in order. For example, in loop quantum cosmology, space is quantized so that there are no singularities. The universe doesn't collapse to a point. Instead, it hits its smallest volume and then bounces back up. It looks like time didn't end. It just switched places. The Big Bang is like a reflection of the Big Crunch, which is when space expands from a world that was tightly packed before. In this model, every end is a beginning, but not without a price. The structure may be inherited, but the detail is lost. Like burning a library and building a new one from the ash, the universe might carry traces of its former self, but the stories are gone. The specifics erased in the fire of transition. Mathematicians have found that some models of the universe can keep information even after a bounce. Roger Penrose, a scientist, has a theory called conformal cyclic cosmology that goes even further. It says that the future of one universe is endless and stretched out, and the beginning of the next universe is compressed and low entropy. As the frames of a film clip flow into each other, so does one step into the next. He says that the world may still have signs of things that happened before the Big Bang, but not in terms of time, how it is built, in the light itself. Maybe the prior cosmos was one of many in a great chain, each giving birth to the next. Each one ends so that another may begin. Perhaps this cycle has repeated not twice or 10 times, but infinitely, and each time something small is carried forward. A singularity dense with meaning. A field loaded with potential. A pattern that, when released, would bloom into galaxies and minds. The final seconds of that universe might have been unimaginably hot, bright and violent, but they were also creative. Birth pains of a god. Mythological echoes of a violent origin. A long time ago, people looked up at the stars and told stories. This was before science gave us binoculars and particle reactors. Stories about violent, catastrophic and holy starts, not ones that are calm and orderly. The universe did not start with a whisper. It screamed in these old stories. It was bleeding. It fought to stay alive. In a strange way, those stories might have been true. Creation myths from different societies, separated by countries, oceans, and ages, all have the same main idea. The world was created from destruction. There is a death. Chaos is broken up. A body is cut up, killed, blown up, or dissected. And out of that bloodshed comes order. In the Norse tradition, the world begins when the primordial giant Ymir is slain. His flesh becomes the earth, his blood the seas, his bones the mountains. His skull forms the sky. Creation comes only through the annihilation of something ancient and primal. In Hindu cosmology, Shiva, the god of destruction, is not separate from creation. He is creation. His cosmic dance obliterates the old universe and births the new. Time, matter, and life are not independent. They rise out of his destructive rhythm. The Babylonian myth of Tiamat, the goddess of chaos, tells of her death at the hands of Marduk. He splits her body in two. One half becomes the heavens, the other the earth. From her corpse, the world takes form. In Egypt, the world rises from the formless waters of Nun when the creator god Atum emerges in solitude. He creates through an act of separation and tension, dividing the elements, carving order out of the void. Even in Genesis, the biblical story of creation begins not from absolute nothing, but from a formless deep over which the Spirit of God hovers. Let there be light is not just a command, it's a rupture, a dividing of light from darkness, water from land, time from timelessness. The Big Bang was not peaceful. It was a cosmic eruption, a singularity blooming into space and time with temperatures so high that matter couldn't exist. Particles collided, annihilated, decayed. For the first fraction of a second, the universe was not a place. It was a war of energy, a plasma of uncertainty. The first laws of physics did not emerge gently. They crystallized out of chaos, like a storm freezing mid-rage. Symmetries broke, forces split. The Higgs field turned on. The fabric of space chose an identity. It became something it wasn't, because it could not stay what it was. What they did wasn't an easy act of making. It was change by falling apart. It's something the world has always done. Breakup is where stars are born. Big things die and turn into black holes. Atoms are made when dead suns explode. We see over and over that destruction comes before creation. Is it any surprise that our ancestors thought the world began when a god died? Some mythologists, like Joseph Campbell and Carl Jung, believed these myths reflect archetypes, deep psychological truths embedded in the human psyche. But perhaps they are more than psychological. Perhaps they are intuitive reconstructions of the cosmic story we now begin to uncover through science. Could it be that, at some unconscious level, humans knew that the world was born from chaos, that there was an echo of that first rupture embedded in the mind? Or perhaps the mythmakers weren't guessing. Perhaps the stories were symbolic records, passed down from a prior civilization or a prior universe that understood what it meant to be born from fire. The patterns repeat for a reason. And now that science is catching up, we are beginning to understand those symbols anew. The Big Bang may not have been a single isolated event. It could have been the last moment of a previous cosmos, transformed into the first scream of ours. It may have been a dimensional collapse, a vacuum flip, a cosmic scar unfolding. Whatever it wasn't peaceful. And just like in myth, what followed was structure, planets, laws, consciousness, the illusion of calm. But deep beneath that calm is a memory of rupture. The laws of thermodynamics, the arrow of time, the expansion of space, all of it flows from a singular fracture, the end of what came before. That means the myths might not have been just stories. They might have been the first physicists. Maybe they used a figure of speech to tell us what mathematics are now trying to explain. That life is violent, not because it is cruel, but because it is born. That everything we are came from something else that had to end. That gods have to die so that worlds can start. So, was the Big Bang the end of something else? At first there wasn't nothing, but there was something strange. There wasn't quiet. There was noise that can still be heard in the sky. Not peace, but stress, heat, and an unbalance. It's not a start, but a change. It becomes more and more clear that the Big Bang was not a single clean start as we learn more about quantum theory, astronomy, and chaos. For generations, the Big Bang was treated as the ultimate starting point. The model tells us that 13.8 billion years ago, all matter, energy, space, and time expanded from an initial singularity, a point of infinite density and temperature. That's the traditional view. But this singularity wasn't just a mystery, it was a problem. Our equations break at that point. Time loses meaning, space folds into contradiction. It's not just that we don't know what came before, it's that the question itself seemed unaskable. Today, the physics community is filled with frameworks that don't just allow for a pre-Big Bang state, but demand it. Ideas like loop quantum cosmology, conformal cyclic cosmology, ekpyrotic models, and vacuum transitions all point to one conclusion. The Big Bang is not the ultimate origin. It's a boundary, a membrane, a veil, and beyond it, something else waited, perhaps collapsed, perhaps cracked open, perhaps gave way to us. But this isn't just about theoretical physics, it's a change in how we think about being alive. First, let's look at the proof. There are tiny scars and whispers all over the world that make it look like it has memories. There are some bumps in the cosmic microwave background. It has strange things in it, like the axis of evil and the cold spot, that can't be explained. Even though they were only recently found, gravitational waves could finally show patterns that are too big to fit into a single cosmic chapter. Even the universe's initial conditions are suspiciously non-random. Why did the cosmos begin in such a low entropy state? Why does the arrow of time move only forward? Why are the constants of nature so finely tuned that even slight alterations would make atoms, stars, and life impossible? These questions are usually pushed aside with philosophical shrugs or anthropic reasoning. We see the universe this way because only this kind of universe can be seen. But what if there's a better answer? What if our universe inherited these features? What if they're not accidents, but artifacts? We are not starting from scratch if the Big Bang was the end of an earlier universe. We're starting with the pieces of an old thing, and those pieces have shape. Think of the old world as a closed loop that is collapsing in on itself. Its structures are being crushed, its rules are being folded, and its energy is being gathered. Or think about a bubble that is in a metastable vacuum state that finally tunnels into a lower energy state, giving birth to a new field of physics. Or picture a universe that was pushed to its limits by dark energy and torn apart by the Big Rip. Its fabric finally broke and was rewoven into something new. In each of these endings, there's violence, a rupture, but there's also seed, something that survives. Maybe it's geometry, maybe it's symmetry, maybe it's information. Many quantum scientists think that information can never be lost, so the old world didn't go away. It was squished, locked up. Its information is written into the quantum fields that make up our world. Every particle could have evidence of structure from a long time ago. Every force could be a middle ground between the rules of today and those of yesterday. Chaos itself might have something to do with this. According to the second rule, entropy, disorder, grows over time. But if our world is part of a cycle, then it started out with low entropy because the last cycle finished with high entropy and was reset, like starting over in space. Even though the RAM is empty, the design of the machine is still there. Roger Penrose's conformal cyclic cosmology puts this into sharp relief. He proposes that the end of one universe's infinite future becomes the next Big Bang. After everything has decayed into massless particles, time loses meaning and the geometry of space can be compressed into a new beginning. The past and future link not through continuity, but through conformality. Scale becomes irrelevant, and so the infinite is mapped onto the point. Other models, like bounce cosmologies, avoid the singularity altogether. Instead of a beginning from nothing, the universe undergoes a compression, reaches a minimum, and then expands again. This preserves causal continuity, meaning that something came before, and its fingerprints might still be here. The most scary thought, though, might be that our world came into being from death. One such model is black hole astrophysics. In a higher dimensional place, a black hole collapses, and our world is inside it. The singularity wasn't a failure. It was a place where babies were born. The pressure, being alone, and the event distance weren't obstacles. They were the limits of development. From this point of view, each black hole could be the birthplace of a new world. Also, our black holes might be making other universes right now. A universal family tree, with each universe giving birth to the next and passing on structure like DNA through a web of gravitational links. Even simulation theory circles this idea. If our universe is a rendered projection, a holographic output from a deeper computational realm, then the Big Bang might have been a system reboot, a software update after the last reality crashed. Not random, not divine, but designed, in some unknowable sense of that word. Whatever model you choose, the common thread is clear. The Big Bang is not the alpha, it is the omega of something else. What does this mean for us? This means that we are not living in the beginning of time. This is what we are living in now. Every step we take is on ground that is very old. We could find echoes of things that happened a long time ago in every photon we see. The rules we follow, like the speed of light, quantum spin, and conservation laws, may have been passed down from a world we will never see. It's possible that this won't change anything in our daily lives. The sun still comes up. Atoms still stick together. There is still pull. But this is important for our understanding and search for meaning, since it changes how we think about the universe from a wonder to a result. It's not a one-time gift. It's part of a longer pattern. It was very loud when the Big Bang happened, but it could have been an echo. From worlds that collapse and universes that bounce back and forth to old models and gods that have been lost, the end of one cosmos may have given birth to the next. It's possible that the truth is still out there, hidden in background radiation, quantum ghosts, or even within us. That's the point if this trip left you with more questions than answers. If you want to keep exploring the unknown, subscribe to Beyond Horizons, because every end could be the start of something new.